I'm going to be walking around. We're going to have the class. We're going to have the class in here, and then we're going to. At some point, we'll go outside, and I'll describe the self-built collector out here that I made, and then we are going to take 20 minutes or so and go up to the residence up here across the street where we have installed a commercially purchased, or the parts were made, manufactured, and we installed that in a residential system here, and myself and Mark here was our intern, so he helped me greatly on that. So we'll have that. You can see that whole system, how it works, and what the parts are and all that. The class is really going to be. It's not. It's difficult to tell people on the website exactly. We only have a little paragraph we use. But what I'm trying to do is cover all the bases. I mean, we are going to spend some time. I'll explain how, and we'll even do a little hands-on on building that one back there. That's a very inexpensive, workable, fairly efficient collector for the fact that it's homemade and just store parts. The commercial collectors are pretty broad range. They all get tested. If they want to sell in the United States, they have to be. It's like a UL testing. They really need to go through a testing so they can be graded against each other. In other words, if a AET company wants to compare itself to Spartan company, they have to have a grading system. So they all get graded, it's a range in there too. They're generally pretty efficient. The AET panels, which we got here, which we chose to purchase, are the actual absorber plate, the guts of the thing inside the collector that actually does the work. That has to be. Every single one of them is tested. They have to be between 96 and 97% efficient, or they don't get sold. They go back and get re-stamped. So I mean that's an incredibly high efficiency for almost anything. So something like this, the little one out there, I mean, you can still make it 90% efficient if you're really careful. Cost-wise, maybe you're talking somewhere between $700 and $1,500 a collector for a extremely good one. That thing might be $100. Is it worth it? Is $100 for 90% efficient better than $1,000 for 96% efficient? Well, I don't. That's your decision. But that's the kind of thing we're talking about. Solar thermal is a very efficient mode of converting sun to energy as opposed to photovoltaic panels, which are great too. But that's a whole different technology. So what I'm going to do in the class is really try to explain why we're even interested in going to the effort of making hot water from the sun, the various ways of doing it, several different systems. I don't want to be too technical. I do need to show you pictures of things here and again. I'm going to talk a little bit about how to site, the tools we need, and the method we use to pick a site or choose a site for your project. If you're going to spend the money on it, you need to know you're doing it in a place that's going to be worth it. If you don't have so many hours of sunlight available because of maybe buildings, trees, or other things blocking your sun window, your solar window, it's not it's not going to be worth it. So you're going to either have to choose a different site, or cut a tree or something like that. And we'll talk all about that. As I said, we'll go up to the house and we'll look at the factory-made components and how that's a fully automatic system and how we tied it into the house. And there are several ways, and they all work. They're all equally good. There's just certain choices depending on the inhabitants of the house and what you're trying to accomplish. There are certain choices about how to set it up to meet your needs the best. Let me see what else we'll talk about. I will talk a little bit if people want to talk. I'm going to cover, or at least mention, why or why not we can or cannot use solar hot water. Can be used for a lot of things. I mean, it can be used for radiant floor heating, it can be used for space heating, it can be used for air conditioning, believe it or not. It can be used for making hot water for your kitchen or house, which is what most people use it for. So there's a lot of different applications. So I think maybe what I'll do is, I sort of got ahead of myself, maybe what I'll do is just go around and how many people are interested in just finding out more about it for potentially doing an installation? Is that pretty much everybody here? Yeah. Is there, well, let me just go around, since we don't have that many people, just figure out what, just briefly why, your name and what you expect out of the class, or why you're here for. So I'll just go you.
I'm Tom Craig. I live in Asheville, and I have a small cabin in Madison County. I've been using a instantaneous gas heater, which when it works, it's wonderful, but that's the problem, when it works.
Right.
And so I'm looking, I have a very good solar exposure with some removal of trees, be able to get a very small scale. I'm looking at a small scale solar operation. Yeah. My one concern, I just want to throw this out, is just what you recommend for this climate.
Yeah, okay, we'll go
drain back
and
and all that.
Yeah. And we'll have plenty of, if you have a question, I mean, if you have a question, you can ask me, and if it's something I can put off, I'm going to talk about later, I'll say that. And if not, because we have enough time, I think, to deal with questions. I definitely want, especially up at the house, I would like to have questions, or even after. I'm going to leave time at the end of the class. The last time I did a class, I ran way over, and we still have, we answered a lot of questions, but I still ran over. This time I want to be on schedule, and I want to leave enough time to answer questions at the end. So, and they can be questions on a specific, collector or panel system, whatever, or just generally about solar energy or whatever, even if we delve into the difference between electricity and water or something like that. So what about you?
I'm Saeed Abdullah. I'm with the Lord Zaker in Fairview, North Carolina. I'm doing research on putting a greenhouse there by the end of the year, and I'm trying to learn more about all aspects of heating and ventilation.
How big is the greenhouse?
We haven't decided. We'd like to get something like probably 100 by 30.
Oh, okay. So pretty big, yeah.
Yeah.
Okay. All right. Your name?
My name's Nancy.
Okay.
I'm really just doing my homework. I plan on building a small home, and I'd like to put greenhouse in it, and I'd like to be pretty sustainable.
Yeah. Okay.
I have a house down the road on a farm. I got great southern exposure both on the roof and on a large wall on the southwest side of the house. Mm-hmm. And I'm really intrigued with using domestic hot water and space heating with hot water. Okay. I want to do as much of that as I can myself.
Yeah.
With my man Eric here, who really does all the heavy lifting.
Okay. It's not rocket science. That's the other thing. It's really there. With the software programs available on just probably for free. I mean, I don't think well, of course, we bought software for the siting and stuff, but you can pretty much find a site that will let you do all the calculations without spending money. So that's that's good. And so
my name's Eric Bell, and I'm a builder.
You're a builder, so you can do the heavy lift.
Yeah. I build a lot of small things. I got a place up in Balsam Grove, North Carolina.
Okay, yeah. All right. Good.
Build.
All right. Well, I'll tell you something. Their systems are a lot easier to put in new construction than they are in existing. Okay, let's do here. You, sir, and then.
Oh, okay. Yeah, I'm Al Hester, and we're from Columbia.
Okay.
But we come up here regularly. We have a small trailer up in Hayward County.
Yeah.
So, I mean, we're interested in learning about the possibilities for our home in Columbia as well as for up here things.
Okay. And so you guys are together?
Yep. Yeah. So I'm Terry.
Yeah.
But pretty much the same answer there.
Okay.
My name is Don Johnson, just up north of Boston, and just kind of exploring practically free, cheap, low-tech energy.
Yeah.
It's too good to pass up.
All right. Let's see. How about you?
My name's Jan,
Okay.
and I'm into sustainable type of lifestyle, starting with a maybe tiny house, eventually small top house.
Okay. Sure.
My name is Barry Lohr, and I'm going to be building a house, and I'm studying different systems quite a bit and kind of trying to decide whether I should build my own system or get a commercially developed system. Okay. And I'm interested in using it for radiant heat, floor heat also.
All right. That's another thing, but I can talk about that. So.
My name is Will Schmidt, and I have a small farm here in Mills River. And I'm looking in terms of solar as an integrated system with wood fire and oil backups.
Oh, okay. Yeah. Integrate, so just the solar, the wood fire, and oil backup, the whole thing.
Yeah.
Like we
yeah.
sort of have over here with our central boiler. Yeah. Okay.
My name is Rosalind Whiteley, and I live very close to Alexander.
Okay.
And I have a little cabin that's off the grid. I don't have running water. I just do rainwater catchment and haul water in, haul water out.
For drinking.
And I do have one electrical cord that comes down, and eventually want that to be solar. But I was kind of looking at a batch water heater.
Yeah, I have pictures of that. We're not going to really cover them completely, but I can explain them. Yeah. They're not used here as much because of the freezing, situation, but you can drain them down, but yeah. Okay.
They're not. So in winter, they're not as effective.
No, I mean, they have to babysit them in winter because they'll freeze and crack.
Yeah.
If they're not drained.
I'm Dolly, and I'm new to solar and very curious.
Okay, sure. We'll talk about that then. Sure.
So, Eric, involved with all things solar, hot waters.
You've been here before. Sir?
David Mossberg. I live in East Tennessee, Monmore, a little place south of Maryville. Live off the grid, and I have solar. And I've been bartered for I have a flat collector and some evaporated tubes, just some pieces.
Yeah.
And it's time to put it together. I like the idea of a open loop, but I don't know. I know you have winter, so.
I didn't even really thought, other than just mentioning the evacuated tube collectors, because they're more expensive and they're a little more delicate.
It was small.
Yeah.
Basically a demo.
Yeah,
and
right.
I have a big, so I'm kind of like maybe one should be for the radiant floor and one should be for open for the water. I don't know.
It
There's
depends
so
on
many options.
Their temperatures are a lot higher. Well, they're more delicate for one thing. They're more expensive, but they do create higher temperatures. But once you get into the realm of higher temperatures, you actually lose efficiency because it's like the hotter it gets, the more it wants to get out and just go into space. So.
And which one, if you had a closed loop and an open loop, one for radiant floor, one for, let's say, would one be better for, would that promote the breakdown of the antifreeze, the evaporated tubes?
Yeah, well, it will. It will more so, yeah. But we'll talk about that, a little later. That might be something we can talk about when we have the questions and stuff. You guys want to introduce yourselves or just?
Sure. I'm Mark, intern with my wife Lauren here at Living Web, and I had a little bit of solar experience. I'm a recovering attorney, and I bartered some attorney work for a solar workshop. Oh no! And then got to work with Richard here. So really cool experience. Glad you're all here. We love it at Living Web. So glad you could be here.
We're cooking a little dinner after the little workshop. We'll stick around for some pasta and pesto and noodles and all kinds of good stuff right from the garden.
Thank you.
You're welcome.
So I want to talk a little bit about hot water about solar, and then hot water versus electricity. For some reason, the idea of solar hot water really hasn't caught on nearly as much as PV, and it's just PV is, I guess it seems more magical. You can heat water with the sun. That's not, even a black plastic bag out in the sun will get warm in a couple hours, and you can wash your hands or take a shower with a 5-gallon bag of water or a barrel or whatever. So that's not really, that's obvious. And the PV is more magical. It's very technical and all that. But actually, the efficiency of the solar thermal is so much greater than the efficiency of the PV panel that it's pretty amazing. Most of the panels now are running somewhere between, depending on the design of a photovoltaic panel, running somewhere between 16 and maybe up to 18% efficient. There are other panels, bench testing and experimental panels and other available specialty panels that are more efficient, but not much more. So we're basically talking about 16 to 18% efficient. So, you can just see from our site back here, 5 kilowatts or 7 kilowatts of power there, how much it takes, 54 panels to make electricity. So that's a lot of money. A solar thermal panel it'll range, but they can be anywhere from about 60% up to 90%. Now before, when I said the absorber part on the guts of the thing, the business part, which is in the middle of the collector, that is 90, 95, 97% efficient. But the entire system isn't always quite that efficient. You have other losses through the frame and heat losses and flow losses and all sorts of stuff. So the entire system is not going to be at that level, but it's still 3.5 times more efficient than a photovoltaic panel. Not too long ago, photovoltaic panels were, one panel was $400, $500, something like that. Now they're down to a lot cheaper than that. A factory-made solar collector, hot water collector, is, as I said, is going to be somewhere starting in the $700 range and going up. I guess you can. I looked around a little on the internet, just retail pricing. I think the cheapest one I saw was $699, and then they went up from there. You certainly can get used ones. Occasionally on Craigslist you see used flat plate collectors, which is just what that is out there and what we have on the house. You can buy them for, I've seen them for $150, $200, $250. If you pick a good one, it's well worth it. I mean, these things are made for a lifespan. They're not warranted for 50 years, but they're made, design life is about 50 or 60 years on these things, as long as they don't get dropped and the glass broken or something like that. So, of course, the copper tubing with hard water, the insides are usually almost always copper, so the minerals in the water will eventually eat away at that copper, but it's a heavy copper, so let me show you. It's not you can pass it around. The walls of that are very, for a piece of copper's expensive. The walls are thick enough that it's going to take a while for water to find its way through that. I mean, just the hard water has minerals in it that just eat away at copper. So.
Is that how big the tubes are?
No. I'll show you. I have one in here, but I'll show you that later. I'm just giving an example. That's actually a piece of the tubing we used to install the system. I didn't want to fool. There's 3 different thicknesses of copper, L, K, and M. And I wanted to use the thickest one we could, so we wouldn't have to be maintaining, wouldn't have to be replacing pipes 6 years from now. Anybody who has copper plumbing in the house in these mountains probably has had an experience of a pinhole leak near the hot water tank. It actually just eats right through the wall, and you'll find a leak. So.
And you're using copper because it transmits it.
Copper, for in the collector, yes, it's one of the best conductors of heat that there is. The sunlight hits it and it will absorb all that and hold it. I can take that. I don't want to forget that I need to. And then in the system, once it's out of the collector part itself, where it actually makes the heat, we use it because the water actually can get so hot from the sun that nothing else will work. Iron will work, but it's too heavy. But any of the plastic pipes, the PEX pipe, the stuff they put in the radiant floor heating, which is also a PEX, any of those plastic pipes, or the conventional polybutyl, which is an older pipe, PVC, even the hot water PVC, it just won't take it. So copper's the only thing that works. Yeah.
Is that even coming off the collectors?
That is pretty much exclusively for what I call the solar loop collector to the tank and back up, and the pump and back up to the collector. So that has to be copper, yeah. If you use iron, it's going to be a rust issue inside, then, which you don't want in the pump. You can put an inhibitor in there. I'm talking now for exclusively for do-it-yourselfers and homesteaders, home builders, do-it-yourself types. If you hired somebody to do it, it's going to be pretty much standard. It's going to be copper, all off-the-shelf stuff, all good quality. But when you're talking about trying to save money, you're going to try to look around for anything you can use. And you certainly can use iron if you want to. It's just going to be heavy, and it's going to be fitting it. If you're
PEX definitely won't work.
PEX won't work. PEX will be fine once it's from the storage tank to your household plumbing. PEX will be fine. In fact, that's what we've got here.
So even back to the collector,
All copper, everything. Even though the temperatures are, even though coming off the collector, it's always the hottest, of course, once it comes out. It goes into a storage tank where within the storage tank, that heat is transferred from the water to the storage water, and then it goes back up cooler than it came out, and gets hot again. But once if you don't use that hot water, let's say you're a single person and you have gone away for a couple days, you didn't take a shower for 3 days or whatever, that water's going to get really hot, and there has to be it'll boil. I mean, it'll get more than boiling. It'll steam. So there's various ways of dealing with that. In our case, we just, when it has an upper limit switch or a sensor, when it hits when that water in storage hits 165 degrees, I think, or 160 degrees, it will stop the pump, and all the water in the collector drops into a storage tank, and that means no more making hot water. You already got enough. We've got 130 gallons of hot water storage in this system up here, which is quite a bit for a residential system. With really, it's only a 1 or 2 person situation. If you had a bigger family, that would be fine. But we have an 80-gallon solar storage tank and a 50-gallon conventional water tank, which I purposely tied together. And some of this, I will admit, I'm playing with it. I want to see what happens. We're going to try down the road to maybe boost up the heat a little bit and do some space heating with it, which requires a higher temperature. But right now, we're just going to talk about what's up there as it is now. Let's see, what was I was talking about pipe. So it's all copper in the solar loop part. Then we can just use conventional plumbing when you take that tank water to the rest of the house. Nothing different there. So the solar credits, just while we're on the subject, the federal government has offered and is offering, and I don't know what's going to expire in 2018. I think I could be wrong, but I'm sure it'll be reinstated or voted on again. They offer 30% federal tax credits for renewable energy installation of a lot of things. I mean, it's not just solar hot water, but for energy saving. There's energy efficiency programs. There's photovoltaic electricity production. There is biomass use. There is the solar hot water. I mean, there's just a lot of technologies, approved technologies, that they will give you a 30% federal tax credit for. And then you've got a North Carolina, up until December 31st of 2015, had a 35% state tax credit for the same, basically following the federal program. So when the new administration and the elections and everything occurred, they allowed that. That was expiring anyway, and normally it was voted in, approved and voted to extend for another 3 or 4 years, and then they voted again. But with this last administration, they chose not to do anything about it, so they just let it expire. And so we have lost that 35% incentive, which is unfortunate, but
Still effective in South Carolina?
It's effective in South Carolina, and it's effective in other states. Well, not every other state has such a good percentage, but actually it is good in South Carolina, and many of the local North Carolina installers are now opening offices in South Carolina, just in Greenville and Columbia, and well, around here it's going to be Greenville or Spartanburg, but mostly Greenville, just so they can get their customers from there because they've lost some here. It's sort of unfortunate. I mean, on one side, people say, well, if it's that great of a thing, why we don't need the incentives. But on the other hand, so many other things are subsidized that don't need to be subsidized. Natural gas and petroleum and other things, nuclear energy and all that. That if you're going to be subsidizing, why don't you just make it an even playing field? But that's the way it is, and it's still worth it. And actually, in a do-it-yourself situation, the federal subsidies have some strictures to them, and it has to be an approved system. And usually, an approved system means a professionally installed system. But you still can, if you meet the requirements, what they call OG 300, which is the OG 100 is the federal requirement for the collector itself, and OG300 is for the entire system. So if you meet the requirements, you can get the credit. It doesn't have to be a licensed, certified installer. So you can do it yourself. But when you get to the point, like when you start building them yourself and doing all this, you're sort of out of your league. So you might as well just not worry about the tax credits because you're not going to need them. It's so cheap. And that's the other thing is just I wanted to remind you. The class was called do-it-yourself, low-cost solar heating. Not everything is going to be low cost. I mean, certainly it's going to be lower cost than if you hired somebody to do it. So I'm going to attempt to show you, or at least convince you, that you can do most of it, if not all of it, and that there are other options, mainly in building things like that out there, and also in salvaging or scrounging or just looking around for good deals on pumps and controllers and things that will make the system work for you. So that's the goal. So let me see. Maybe I should explain a little bit about how the collector works and why it works. We have, I'm sure everybody's heard the term BTU, British Thermal Unit. A British Thermal Unit is just a measure of heat, a heat unit that we use. We have to have some way to measure it and talk apples to apples. So at some time, several hundred years ago, it was defined in the English system as the amount of heat it's necessary to raise 1 pound of water 1 degree Fahrenheit. So that's all we have to know. It just takes 1 pound of water is what, 8.33 gallons, or one gallon weighs 8.33 pounds. So you can figure it out. So 1 pound of water, whatever energy it takes to raise that 1 degree Fahrenheit, that's 1 BTU. So if we got a system like an electric heater, it's 1,000. Or it might be 5,200 watts or 5,200 BTUs, 1,000 watt system. That's the heat. The heat that makes would raise it up, by that much. So you get an idea of, how things are done here. So the sunlight that falls on the outer atmosphere is something in the nature of 428 BTUs per square foot on the outside of the atmosphere constantly. That's the constant. We don't get to use all that because what happens is it goes through the clouds, it goes through moisture, air pollution, there's reflection involved, just all this interruptions on the way down. So a system in Florida, for example, which is just a good one to use, I think the absolute maximum in Florida from that 428 BTUs, you're getting 290. Say, for example. So in other places you might get 210, 240, 190, whatever, depending on how far north or south you are of the equator. Obviously, as you go, well, it's not, maybe not obviously, but as you go north of the equator, the angle that the sun is striking the ground and the temperature, as you go further north, and as you go further south of the equator, same thing, because their cold happens as you go to the South Pole, will reduce the strength of the sun, essentially. Because as the sun is hitting the Earth at a much different angle, so I just took this little thing because I don't want to, I was told not to write on that. So, if you're at if the Earth's curvature is like this, and the sun's coming down from the equator, that's a direct that's a direct line. But if you're talking about like this, you're going through an oblique path. So there's less energy is actually going to reach its point here than here. And that applies as well, in time-wise, noon and versus say 3 o'clock in the afternoon. So we're dealing with a variety of energy available, and you can find that information from the NREL is a National Renewable Energy Laboratory. The weather station up here at the airport has it available. I think NOAA has it. If you can just go online and look, and there'll be just solar radiation or solar insolation, not insolation, but INSOLATION, and that'll tell you. Usually, you either just punch in your zip code or a city or town near you, and it'll tell you how much energy is available per daily, monthly, annually, seasonally. It's available in different, different ways. Yeah.
That number you said, I don't know, 210 to 290. That's BTUs per hour.
Yeah, BTU. Yeah, exactly. So obviously, if you have a little surface like that, it's not going to gain as much. You have the same energy hitting it, but it's only collecting that much. If you have one as big as that, that's going to be 3 times more. Given the same side by side. So that's basically how we're establishing that. That little panel there outside is a half a panel. I just did that so I could pick it up. Basically, we'll use it here for something, hand washing maybe, or just tie it together with other ones. But I didn't want to make since it's made of wood, I didn't want to make something so heavy that I couldn't move it. So I just made a half one, and we'll talk about that later on. So this energy is coming down onto the surface of the collector, and the collector essentially is just a box with an absorber plate in there, and the box is about 3.5, 4 inches deep, 4 feet wide, and 8 feet long. Yeah.
You mentioned that you can buy a meter and send it out, and it'll track how much sun is.
Yeah, you can do that.
And they're relatively cheap.
Yeah, they are.
They're
Yeah.
expensive. You can set it at any site that you want, and it'll tell you the available energy at that location for a day or a week, whatever long you track it.
Yep.
It's useful if you're going to pick a site.
Oh yeah, it's very useful if you have time to.
Indication of how many BTUs you're
Yeah.
getting in a particular day.
And if you have time to watch it, I mean, like on one day it might be vastly different than another day, or December may be different than July. But I mean, that's a good point. They used to take light meters from cameras, and you could actually make a scale from the output and do the same thing.
And now they're cheap, like $30.
Yeah, they're enough. Yeah.
Little box and set it out where
Yeah.
you can put your collector and get an idea what.
Yeah, no, that's absolutely correct.
And it'll track it over a certain amount of time and download it to.
To your computer.
Software
Yeah.
program that'll give you a little graph of sun intensity over the
Yeah.
time that it's out.
Yeah, that's right. So
So 4 by 8.
well, that's not carved in stone. That's a very common size panel. Come on in. It's a very common size panel. They make panels that are half that. They make little short, 4 by 4. They make 32. This is just one company, and there are hundreds of companies that make these panels. They're not panels; they're actually collectors. A photovoltaic module is a panel, and a solar thermal hot water device is a collector. So that's just technology, or just terminology. But they have a 32-inch one by 7 feet, and just different sizes. But the AE32, which is the number, the one we got up there, is a 32 square foot, 4 by 8, 32 square foot collector.
How do we determine what size panel for DIY that we're going to make?
Well, that's part of this. I'll explain that later. Our siting and not siting, but well, it has to do with siting, but choosing the correct panel. The sun, then there's an absorber. Let me see if I might get my box. Oh, here it is. Inside the 4 by 8 box, there's an absorber plate. That's just a little section of the one that's up in the house there. We can pass that around. The water goes through this is the copper tube. It's fairly small, smaller than the one that I showed you before. And this is the copper absorber. This is electronically welded. That door may be locked. Yeah. There's actually an electronic weld. It's a high frequency AC weld. It's very, very, it actually seals. It's not even a weld anymore. It just makes it part of the, it makes this part of that. So it's firmly attached. And this is only one little, they have about, I don't know how many it would take to make the full panel, 12 of them or something, but you can pass, it's a little sharp, just watch the edges, but you can pass it around. So that absorbs, that little piece right there is what I said was 96% efficient. That's laid in the box. The box is fully insulated both on the bottom and around the sides, and then a low iron glass cover is put on the box, and that's inside of it. The special glass is put on the outside because iron reflects little pieces of iron in the glass, which is, most glass has iron in it. All glass has iron in it, but the more iron in it, which makes it sort of look greenish, the more iron in it, the more it reflects the sun away. So you really don't want that. You want as much sunlight to get into that thing as possible. So when they build a collector, they specify low iron glass, and they temper it so it doesn't break. I mean, you can break it, but it's very difficult to break. And so the sunlight, actually, the radiation waves of the sun, it's a sort of a mid-range. In the spectrum, there's everything from microwaves to long waves, and it's sort of in the middle there. They go through the glass, hit the absorber, and they are converted from basically light energy into thermal energy, and they can't escape out very well because once it's in there, the longer waves just don't come back out again. So the heat stays in there, and the copper is extremely good at retaining the heat. So
Greenhouse effect.
the what?
Greenhouse effect.
Yeah. Exactly. It goes in, but it can't come out. So and then the copper is there to absorb every bit of it can. Yeah.
And that's painted black so that it will absorb more?
Yeah, the darker they've experimented with different colors for many years. A black surface, a dull black surface, a flat black surface is the most efficient absorber surface and color there is because it doesn't reflect, well, it's the least reflective of anything. So that's what we don't want it to reflect anything. We want it to suck in as much as it can. To make it a little more complicated, all the collectors, with the exception of the one we built, except we can sort of do it with the one we built, is what they call a selective surface. It's not just black, but it's also the way the surface is made is many little granules of imperfections on there. Like imagine like grains of sand being put in with the paint. So it's bumpy. You don't really even feel the bumpy, but it's in there. And what that does is it refuses to let whatever wants to get out, whatever little bit wants to get out, it's going to hit something else on its way out next to it. It's like having little mountain ranges, and the light might hit, and then it tries to bounce out, but there's another mountain it hits before it gets out, so that one will absorb it. So it's called a selective surface, and they've engineered that very specifically, so that helps considerably.
Is that type of paint available?
Yeah, there is thank you. There is a commercial paint available that is called selective surface solar paint, but it doesn't, it's almost, I shouldn't say it doesn't work, but I'm not sure if it's worth spending the money. You can just buy flat black barbecue type paint. It'll do almost as well.
And it will tolerate the heat.
Oh yeah, that's the whole thing. You have to have a high temperature paint. Yeah. So
how important is the glass part in the DIY installation, and how do you select that glass part?
That's going to be a matter of what you can afford. I have thought, I did think at one time that the thermal pane glass for the sliding glass doors, because they're cheap, you can get them used all over the place. I mean, you go to a glass company, they usually probably give them to you, because the used ones. If they're clean inside, but they actually have 2 layers of glass, and that doesn't really work that well. So it's not a good idea. You can order. I mean, you could pay to have a piece of tempered glass cut and tempered. I mean, you can't temper a piece of glass once it's. You can't cut tempered glass, so they have to cut a specific size, and then they put it in an oven and temper it, and then they sell it to you. That's pretty expensive. You can do that, but it's still pretty expensive. I would imagine that by the time you did that, you'd be better off buying a regular collector, because they already have, they buy it by the by the hundred. So
But if we can get tempered glass.
Yeah, if you could,
so
okay.
We can get it in the right size.
Right.
Wherever it comes from. Is there some way to test whether this glass is okay for using in this application?
The only way to do that is if you can find out from the manufacturer what the iron level is and compare it to the iron level of a traditional solar collector, which you can get from the manufacturer. So you could do that. The way I would do it, and the way I did do it, is we'll buy a polycarbonate sheet. It's just a thermoplastic sheet. There's various, it's mostly used for greenhouse coverings. Not that kind of plastic, but it's a stiff, hard. Kalwall is one name brand. It's a fiberglass reinforced plastic. PVC styles are made. That's a Sunlight. Home Depot has that stuff. You can drill through it without cracking it. It has really good light transference. It has a very high UV ultraviolet. It withstands ultraviolet rays, so it doesn't deteriorate. So that would be a good choice, and that's why I don't like the ripples as much, but that's the way it comes.
So
and
stay away from glass. Stick with polycarbonate.
I think so. Yeah. Yeah.
And what was the name? Caldwell.
Kalwall. Kalwall.
And is that
Kalwall.
available from Home Depot?
No, you have to get that from the easiest source for that is a company in New Hampshire called Solar Components, and you can just Google it. And they'll roll. It's actually rollable. I think they ship it in a roll. They might have a sheet. I'm not sure how they do it. And they're not the only supplier. You can just look for polycarbonate glazing supplies, and you'll probably come up with a whole bunch of shippable stuff.
Thank you.
Yeah. Okay. That's important because you'll need that. So the big deal is when we're building your own panels is you want something you can cut without cracking it. You want something you can drill a hole through without cracking it, and you want something you can rely on not to deteriorate in the strength of the sun, so that the UV rays won't get to it and make it brittle and disintegrate. So and all those features apply to what's used in greenhouses. So that's a good place to look. Greenhouse supply companies, places like that. It's not the kind of thing that you just go down to Valley Ag down here, the farm supply, and get. But you'll have to, like Mega Greenhouse stores or one of those big greenhouse suppliers will probably be able to help you with that. So basically, that's how it works. I mean, we've got water being sent through the tubes. There's a manifold, and you can see it out there. There's a manifold. It's essentially a tube at the top, a tube at the bottom, and then a series of tubes up and down, and they're all connected. So the water goes in one end and has to go through everything before it leaves. So as it goes through, it just picks up all the heat from the copper and comes in cool, goes out hot. Keep on doing that, it's going to come in a little warmer, and it's going to go out hot, and it's coming in warmer and warmer, and eventually, I mean, there's going to be a differential, but it's going to come pretty close, unless you draw hot water. Once you turn the faucet on, you're going to be using it. But the systems generally are designed to shut down when the temperature coming in is pretty close to the temperature going out. So.
Is it possible to buy those fins
Yes.
like that in pieces? That you
Yeah,
can...
Thermafin company. The company that makes this is AET, American Alternative Energy Technologies in Florida. They manufacture the collectors, and they also manufacture their product called Thermafin. And I'm pretty sure you can buy it from them. I don't know if you can buy it retail from them, but I know they sell it. They sell it for other manufacturers who make their own frames and their own glass and all that, but they use the Thermafin absorber.
Is that the best way to do it if you're doing it yourself? Just buy that stuff?
I think I don't know the cost of this stuff, but if you can't get it from AET, somebody else makes it. You can price it out, and it would be a lot easier, because I'll show you how we do it, and it's not that easy. It's time consuming, and it's not as efficient. Yeah.
Could you say the name of the company again?
AET, Alternative Energy Technologies. Okay. Let me just see that. I think I have a little notebook here. Let me see. So They're in Florida. That particular company is one of the few, if not the only manufacturer, American-made, domestically produced solar collectors and components. And he built his company up by buying out. There were, a number of. I think he said he bought out nine different other manufacturers that just, for whatever reason, couldn't continue. So he just built one big company out of a lot of little ones, and they're the main suppliers. Chinese people make. China's a big supplier of solar collectors. Israel's a supplier of solar collectors. Greece has some manufacturers. You see where this is going. The main place in the Mediterranean where they use a lot of solar hot water. Spain. I mean, so they're all suppliers, but AET is the only domestic one. So shipping and all that stuff comes into effect. And they're also pretty much handmade. I mean, I was at the factory. They have a, it's a small by manufacturing standards crew, but they all just the absorber things are more or less automated, but the actual assembly of these things and everything is handmade, hand tested. Each individual thing is tested, so it's a good product. So I wouldn't get away from, I wouldn't avoid buying from them. But as I said, if you get a used collector panel from Craigslist or Iwana Paper or whatever, you can actually look up the specification of that collector by the number on it to see who made it and how efficient it was and when it was made and all that kind of thing. So you can do that, and I'll talk a little bit about that too, how you can find it. So let me see. Maybe I can try not to. I purposely did not put together a PowerPoint presentation because it's just too structured. Now I want to just get to talk about things that we want to talk about. I'll go over the system here, and then we can spend some time maybe either talking about siting, or we can talk about siting, and then we can do talk about the panel too back there. We got the pointer. So there's the collector up there. There's the collector here. I'm going to use the pointer. And the solar loop is separate from the house loop. This is your normal hot water tank in the house. And we don't have to really worry about all these valves right now. I mean, if people have questions about any of this, I can explain it. But just for now, I can just talk about what's going on. That's your normal hot water heater that's in the house. And then to put in a system here, we get a solar storage tank or a solar reservoir. And that's another highly insulated, usually a little larger. That might be 40 or 50 gallons. This one's usually 80 or 120 gallons. Inside this one is a heat exchanger, copper tubing coiled around, and an outlet. The water that goes through this system does not touch the water in this system. So this has its own, I don't know if everybody can see it, but this has its own flow. The pump, there's a pump here. Maybe I can just do it here. Pump here. Can everybody see the little dot?
Yes.
Okay, so I won't use my finger. So let's just start at the pump. Well, first of all, this entire loop, all the way here, through here, down here, through that heat exchanger and back up to the pump, is pure water. Sometimes people put distilled water in there, which actually is a good idea, but it's usually just water. And so from the pump, once the system is filled, from the pump, it goes up, gets pumped up to the base of the collector, goes through the manifold in the collector. It's a series of H's basically, and then it comes out here. And in this particular one kind of system, it actually gurgles or drops into a drainback reservoir. It's a 10-gallon tank right there that has air. The tank is never full. It's only about 2/3 full when it's working, when it's pumping. And then the water that falls into that tank drains or gets pumped into the base of this heat exchanger, never touching the water. The waters never mix. It's just the heat gets transferred from this coil into the water surrounding it. And then and when that happens, the water that came in really hot is now cool when it comes out because all the heat's been drawn out of that loop. So it's not, when I say it's cool, it's not 60 degrees, but it's a lot cooler than when it came in. So then it goes up here as cooler water, hits the collector, gets hot, everything happens all over again. Yeah.
So,
Oh.
I'm sorry.
No, go ahead. You ask, and then he'll get it.
The larger tank.
Which one? This one?
No,
That one. Okay.
that's a closed system going through.
That is Yeah, but it doesn't. The water in that tank does not touch the water in that loop.
Right. And
Okay.
how big is that tank?
80 gallons.
That's the 80.
Yeah. Back here with that one question. Well, sorry. You had a question after, and I'll get you.
Are all the systems that you would recommend have a pump, or can you use a thermal siphon?
There are thermostat. I would recommend in this climate that we use a pump of some kind, a pumped system, but you don't have to. One more, and then I'll get to you. Yeah.
Does the pump run constantly?
Yes.
Or only during the day, or what?
Yeah. Let me explain that when I go through the actual working of it. Yeah.
The small tank here, is that just a drain back tank?
It's a drain back tank. It's called. There is no expansion tank in this kind of a system. It's the simplest. The reason I chose this kind of system for this application and the workshop was because we purposely labeled this as the simple as we can get it, simple and as cheap as we can get it. So we stuck with the simplest system. Yeah.
So there's steam in that system that forms from the...
No, it's not going to be steam in there. No, I'll tell you, and I'll explain why. Yeah.
If it's water, so you drain it in the winter, you don't use it.
No, I'll explain what happens. It'll drain, but not like that. And it all connects to what you said. So I'll talk about that part first. I guess you can see the dot. So it's gurgling in here, and it's a little pond or pool. Well, not pool. It's 2/3 of the little tank, which is only about that round and about that tall. So 2/3 of that, or maybe 6-7 gallons, is always the supply for the loop below it. This tank, this loop functions. Up at the top here, see that little wire? See that little dot and that wire going down? And then down here at the other side, and that in our system that's down actually in the tank, but it doesn't really matter, is two thermistors, or they're reading the temperature as how hot it is up here and how hot the water is down here. When the water gets, let me see, we start in the daytime. In the daytime at noon, say, it's going to be as hot as it's going to get, and that pump's going to be going like crazy. It will go as long as there's a high enough temperature in that collector to make hot water. That pump's going to work. As it gets towards evening, especially in the winter, as it gets towards evening, and it cools down pretty quickly, when that thermistor tells us that the temperature has reached, it's variable, but it might be about 110 or 90 degrees or something like that. When that happens, or even lower than that, you can set this. It shuts the pump off. Once the pump's off, all that water drains back. So it's, for your question back here, it doesn't happen just in the winter. I mean, every day, that thing's gonna stop and drop back. All that water's gonna drop back into that little tank.
Does that fill up then?
It only fills up to 2/3. I purposely did not fill that tank up to the top because you want a little air buffer in there, because it won't drain if it doesn't have.
I'm just wondering, if there's 2/3 in it and more drains back into it, where does the more go?
Back into the. It's set up so that it can't. Let me see if I can explain that. This is already filled with water, so it sort of reaches this level at this point. That's where it sets at. There's no incentive for it to push up beyond there, because this is just the level that it's set at.
But I was just wondering, the way maybe I misunderstood, that when the pump shuts down and it drains back, and if it's like that already, where does it drain to?
Both. The water in the collector drain because this tank is not. When it's running, that level is not at 2/3. It's at 1/3 when it's actually running, and then when it stops, it fills it up to about 2/3 or 3/4, something like that. And you'll see it over here when we see it. Yeah.
It seems like if it stopped, it would only be draining left leg of it, like that other part's downhill, so would it create a siphon?
No, it's this, when you set the panel on the roof, not only does that have to be tilted that way for the reasons of getting the best sun, but it also has to tilt, that end has to be lower than that end.
Right, but it seems like you'd still have water on the blue side, would hold water overnight, would it not?
That'll get pushed up to here. If it's going to drain, in order for it to drain, what gets pushed here is going to shove the water up into. So it's happening, not only is it falling this way, but it's pushing it up that way too.
Seek a balance.
Yeah, it seeks a balance, right? So water seeks.
I'm assuming the pump either has a check valve in it, or once it
No, there's no check valve. You don't want a check valve in that pump because once it shuts off, it's just a open system.
So this
Yeah.
10-gallon drain back tank, it's just a 10-gallon tank of any sort we could use for this purpose.
You could take a beer keg. That'd be a great use of it. If you could put a sight glass in it, and you don't even really need a sight glass, but it's nice to know because you have to know how to fill it. You have to know how high to fill it. Right. If you fill it too high, it's not going to work. If you fill it too low, it's going to suck air. So you have to have it, right. But you could take a small pony keg. I don't know how many gallons is mine. I make beer, so it's 15.5 gallons. That would be a perfect one. It's stainless steel. If you could, get some fittings in there, it'd be great. You had a question, Dan?
So from the, you called it a drain back tank?
The little tank, yeah.
From that point below needs to be in an insulated.
Yeah, that's what I was just about to say. That's what the question he had. All this stuff goes on the roof. Well, I keep on walking over there. The roof is at that level here, or somewhere in there. So everything below this is in a tempered area. It can be close to freezing. In fact, it could be in a place where it might freeze. The air might be, in around 32, but because that water is still going to be pretty hot in there. In that situation there, the room normally doesn't get into 20 degrees or anything like that, so it's safe. So the whole drain back idea is that if there's no water to freeze in the collector, it can't freeze. It's not there. It's not there to freeze. So that's the whole concept. Yeah.
Not to confuse, I have a little 12-volt water circulation, hot water circulation pump with a little panel. These are pieces that I acquired, but is there a way to use that and not use the controller where at night the pump stops with the water fall?
If you remember to shut it off at night every day.
Is there a way to make it automated to go on and off with the
Well, you could buy the thermistors and
Right about DC powered solar pumps.
Well, that's the other way of doing it too. Yeah.
Well, that's what it is. It's a DC pump.
Yeah. When the sun shines, it's going to pump, and when it doesn't shine, it's going to drop it.
It's not going to be hot if it's not.
Yeah.
Yeah. Sun pumping.
The trouble is,
It's backwards.
But would it prevent the drain back? I guess is my question.
Well, that depends on the design of the pump. I don't know. I don't know what kind of. If that pump has a check valve, it will prevent the drain back.
Is there a place on that loop that you could put it to not where it wouldn't cause you?
If it doesn't have, if that pump has a check valve, it has to be removed from the pump before, no matter where it is in the system, to make it work. And you can test that just by blowing, or pumping water through the pump both ways to make sure it goes freely both ways. Okay, let me have questions here. Let me. Okay.
Help me understand how much water might be in this collector you've made.
About a gallon. Oh, that one there? Yeah. I think the big one. Those pipes are pretty small. I think it's 1.1 gallons in the one collector.
4x8. One whole big 4x8 one. It might be only 1.5 gallons at the most.
Yeah.
That's interesting.
Yeah.
What would I have a solar photovoltaic system. What would be the draw of a water pump for a small, just a range?
Oh, something like that would be very minor wattage. I mean, it would be like down in the, depending on the pump, of course, but it could be a fractional. Some of them are 1, 2 watts, something like that, as little as, Yeah. Watts, little, very.
Not kilowatt.
Yeah. No, watt. I mean, the higher, that pump is only designed, or not that one, but the one at the house is done 26 feet. Is as high as it will pump, but it still is. We can look on it. I don't happen to remember
13
what.
psi.
Yeah.
A pump that would
Yeah.
work against 13 psi
Yeah.
head pressure in that.
At that level, yeah. They, back in the day, they just used to take a pump that would work, and in a off-grid system, it would be very absorptive of the, in other words, it would eat up a lot of power. So the companies saw a solar market and said, we need to design a pump that's going to do this kind of stuff and be a lot less energy, a lot more energy efficient. So they did. We're talking about just small wattages, really. Well, it could be 2, 3, whatever, but it's,
Does it matter how fast it's moving the water?
Well, it does. It does. These particular ones that they make for the systems are variable speed. So in the beginning, in the morning, assuming, well, not assuming, because if it's working, it's all in the little tank. In the morning, it's going to need to have a high flow and a good boost to get it up there. Once the loop is filled with water, then it varies itself down to a slower speed, and it doesn't draw as much energy. So that's how that is. Now you could use, you can use a pump if you don't mind it taking a while to get pumped up in the morning. Then you can use a smaller pump, but it's hard. It has to get it up there. Yeah.
What reactivates it after it drains down in the morning? You say.
Okay. Yeah, that's part of the discussion. Well, now in the morning, the sun, say it's 6 o'clock. It's just dawn. The sun comes up, and now this collector is going to get hot. And then eventually it's going to get so hot that thermistor tells the controller down here, hey, it's ready to pump. Go ahead and turn the pump on. Because the temperature is now at 110, 115 degrees up there.
Yeah, but that was a high limit thermostat that turned it off, right?
Well, actually it's the same. The difference between this one and this one is it's actually what's controlling the whole circuit. Let me see what the settings are. I don't remember exactly what the settings are on this thing because we just got it. But that pump only functions if the temperature up there is above, let's just say 110, and then it'll kick in. But then when it falls below and it's getting ready to freeze, say in the winter, then it stops the pump and all the water drops down. Yeah.
If it's a closed loop, and if your water tank was below your panels, could you not just get it by with
water tank
as your drain back?
Tank below the panels. Okay.
Yeah, well, let's say that's on your roof
Yes.
and your water tank's below it. Could you cut out the drain back tank and just not fill up the loop as much, so you have the water space in your...
No, because that would incur. I think that would encourage airlock. You need that head space in a bigger way to get that big burp out of there. Okay. Yeah. Now there's other systems.
If you reverse and put the coil on the house side and use the tank as the hot side, you can do that. So the coil was actually connected to the hot water home side.
Yeah.
And the tank.
Yeah.
The hot. Yeah. So if you reverse that system, then you could do that. And then you just essentially have a big tank of hot water.
Yeah. Right. So some other systems, and I don't want to confuse the issue, but other systems don't have the heat exchanger there. They have it in there. That's another way of doing it. That will. Some systems then require 2 pumps, and I didn't want that either because it's a little bit more efficient, but it's more electricity too, and so it's easier just to have the single pump and just let it go at that. This system is designed too when this water gets too hot, when the water in the tank gets too hot, which can happen. The sensor in there, see that one that actually in our system is down there. When the tank water gets too hot, it will also shut the system down because you don't want any more heat coming in. So it just drains everything back, and no water, no freeze, and no boil. So the other systems like glycol loops, there are non-drain back systems that use a antifreeze in the loop, and they're called glycol loops. They will get extremely hot, and there's various ways that they have to have backup valves, pressure release valves, snifters, vents. They have to have all this kind of stuff that has to be built in for safety reasons. That is just asking for trouble because the hard water we have around here eats those valves up regularly. So there's a lot of maintenance involved with that.
In the drain back system,
you don't need any of that stuff. So it's not to say that you're never going to have trouble with the pump having junk in it or all that, but I mean it's just less stuff to go wrong. It's really the simplest. It's a really good design.
And it's always higher up in the water.
That's the drawback. you have to have, it has to have a, your collectors have to be at a higher point. So what do you do? How do you deal with that when a customer's, I mean, if I was a professional installer and I really want solar hot water, and he's got a house with a situation where he really can't put, can't have the tank, he wants the collectors on the ground, for example, you just don't have roof space, or he doesn't want to penetrate the roof. The only way to do it that way is to then, if he has a basement, or dedicate a basement space, if you can put the collectors on the ground as long as your storage and your other tanks are below that. And the only place to do that is a basement. So that's possible, and it happens all the time.
Is there a minimum amount it has to be below?
No. No, the maximum amount is, for most systems, is 26 feet. But you can go a little higher with a better pump, but you're going to be eating more electricity. Then eventually, as you get up to, if you have like 50 feet, you're going to start getting into problems with airlocks and water coursing through a closed pipe like that. You really don't want to have a system that's like 100 feet, the panels are way up,
I'm thinking of lower, I mean 10 feet.
Oh yeah, 5 feet would be fine. You can, it doesn't have to, it just has to be lower. The minimum requirement for a pipe to drain is 1/4 of an inch for every foot. So every 4 feet of pipe, you have to have 1 inch of drop. So that's not much. We have a lot of vertical, almost all vertical drops for that system. Only one pipe is at a maybe 3 to 4 inch per 4 foot drop. And I may go back and correct that. It's working fine, but I may correct that eventually to drain the system. Yeah.
So the thermistors, they register the change of temperature between the two of them. But in the morning, what makes that start again? Is it just a timer?
The sun comes up and heats up that part and tells it, you're ready to pump now. We're hot enough to start the pump, is what it says.
Even though there's no water in that line right now?
Well, there's no water because the pump hasn't started. But once the pump starts, it sends.
The pump always has water in it.
Yeah,
It's low,
right. The pump is always ready to go with water in it. Yeah. It's always at the bottom of the system.
So the question is, the thermistor, is it reading the temperature of the water at the top?
Well,
when the water's gone, then it's basically...
In the morning, it's reading the temperature of how hot that copper gets.
So it's a conduction reader.
Yeah, it's a conductive reader. Yeah, right. And then once the water hits at that temperature, when I turn that thing on, say at 10 o'clock in the morning, if I unplug the controller and I plug it in at 10 in the morning, and it starts up, I mean the pump doesn't start, but the controller starts up and tells me what the deal is as far as what the temperatures are. It'll say 158 degrees, of course, because that copper is hot. But then because it's 158 degrees, it says turn the pump on. Within a minute, that cool water, or the cooler water, is going to hit that pipe, and it's going to drop that 158 down to 110 or 119 or something. But it's still going to remain to be on because it's above the threshold.
So in the big picture, is this about the simplest system you could do for a DIY?
No, the batch hot water systems and the one that, who was talking about that back there? Yeah, that's the simpler, but it doesn't have any pumps or anything. That's a thermosiphon system, or a batch where you actually have the tank on the roof with the collector. But they're prone to freezing, so you.
That's what I'm saying.
However,
take into account that you want to use this year round, and this is about as simple as you can really get.
This is a simple and as simple and as a fail-safe system as you can have.
You're going to need some electronics and some control system, even in a DIY system.
Yeah, that little gizmo there is about $100, so it's not like the end of the world. You can go online and do a hack, or some kind of a Instructables is a website where they tell you how to build a lot of little electronic things, making.
Raspberry Pi.
Yeah, right, Raspberry Pi, all that. Yeah, so there you go. So that's that. But I mean, it's, for most people, just spending $100, $125, $160 on that part is going to be okay.
Sir?
Yeah.
Is there a requirement for the drain back reservoir, how much higher it's got to be than your storage tank?
It's usually placed on top, as far as where it's normally placed, it's anywhere between there and there, but it does have to be above the storage tank.
That and below the other pipes coming out of the collector. Doesn't matter how far, how big, like he was talking about, if you've got a situation where you've got the collectors on the ground and maybe a basement down here you're coming into with the storage tank, you can just put that above the storage tank.
Yes, because it has to be above the top of the heat exchanger coils to be able to drain into the heat exchanger coils. That's all.
And you'd have to be above your pump.
the pump is always the pump is always, this picture is a little misleading because the water pump on most systems is not that high. It's usually down here someplace.
Right.
It's got to be above, if you put your pump all the way down the bottom, it's got to be above it or you get airlock.
Right, exactly. The only bad thing about putting the pump at the very, very bottom is that that's where the debris also goes at the very bottom. But usually they mount it up just a little bit off, and so it's,
He was saying you just can't put that dump reservoir on top of the solar collector and have the pump up there and when it bleeds back down, you have a dry pump.
Right, you have a dry pump. It has to be wet at all. The pump will burn out if it doesn't have water in it. Yeah. Okay, I want to complete the rest of this. So we've got a tank here. Now we have a big tank full of hot water. And so what we're doing, this duplicates the system in the house here. You actually don't really need that. You can get rid of your existing hot water tank is not going to be nearly as efficient as far as installation as your solar tank. So in many, that's okay. In many systems, the normal residential hot water heater is completely removed, and that right there is your new hot water tank. So you just hook your cold water supply into that, and your hot water outlet. The cold water supply is here, hot water outlet here, and just go to town, just like just plumb it into your existing plumbing that's in the house already.
Do you need the overflow valve, when it gets too hot?
In this system, by code, you're supposed to have they all have to have any storage tank that's full of water has to have a temperature and pressure. It's the T&P, a temperature and pressure. So if it reaches a certain pressure, which I think is 150 pounds, I think, or is it 200? Anyway, when it reaches, it pops, and if it reaches a certain temperature, which is 200 degrees, it will open. So it won't be steaming and making a blast.
So as the next step, you're going to explain to us how to maintain the temperature in that tank? So I want 110 degree domestic hot water. So
yeah,
is it the hot loop that determines?
It's a combination of the settings of that controller and what you set in any of these tanks. Both of these tanks actually have elements in them. There's one element in that one, and that has two elements in it. A normal hot water heater has an upper and a lower element. So, for the sake of efficiency, I didn't even put electric supply in that at all. We just left it because this already has a element, right. And actually the residents there, I put in a switch for him so that he can actually turn the electric element off completely and leave it off, so that it never needs to come on, because that tank will store hot water for 3 days 4 days, I don't know, without any electricity in it, without the solar, just anyway.
You're running the domestic hot water here at 100.
It'll run from 110 to 130, and we turned it down to 100. The lowest it would go at 110. Okay. Yeah. The what now?
I just was telling you a time check. It's 3 o'clock.
Oh, 3. Okay. Thank you. So in the system we put up there, I'm feeding the cold water into this tank here, just like in this picture, and then it's feeding solar warmed water into what would normally be the cold water inlet of the existing tank. So that does two things. It doubles our storage, or even more than doubles our storage of hot water. And number two, normally the water coming into your house, hot water, is about 60 to 65 degrees. Now I'm bringing it in at maybe 130 or 120. So that element, especially with one person or two people in the house, that element is probably not going to come on at all. I mean, it might, but I don't really know yet because the system's not, we don't have a good long run on it. Yeah.
If you live off the grid and don't have electric water heater, you just cut it out.
Yeah, you just cut it out and use that right there. You have to have a pump, of course, to get, besides this pump, you have to have a pump to get the water in and out.
Well,
I mean, this pump is for...
Yeah, well, there's pressure on the whole water
Yeah, pressure. Well, whatever it is. Yeah, yeah. I mean, if the gravity, pressure, whatever, it doesn't matter. I mean, as long as there's pressure, that's all you need. There's one pump required to do that loop, and then you have to have pressure to drive water through the system. But yeah, you don't. I would just cut that whole thing off and just use the solar tank, because that solar tank is a better tank. It's built better. It's insulated better. It holds more water. You know, so that's all. Yeah.
Roughly, what's the price of that 80-gallon solar?
That I can't tell you. I've asked the manufacturer, and she did not. She had to go to the owner to see, and I didn't push it. She said they do not make those tanks, and she said we were bound by the manufacturer to not reveal the wholesale or the retail price, because they don't sell them retail. So you know, it's like, well, so what I bought was basically a system. You know, I specified what I wanted, but I ended up buying a system. And she said, if you're adamant about it, I'll tell you. But you know, it's not. Don't tell anybody. And so I don't know. So I didn't want to get into that position. You know, you can find out. Ford, a company called Ford, White. What's that other big company in Tennessee that makes the water heaters? Oh, they have them at Lowe's. Yeah, Smith, A.O. Smith. They all make those solar tanks. So they'll probably be in the, I guess they'd be pushing about $800 range to start. I could be wrong, could be a little lower than that, but I think they're going to be in the somewhere between $600 and $800. Yeah.
If you go with just the one tank, that means all those other little valves that you haven't even talked about yet,
no,
you forget about them, right?
You don't need them. What you do need, I'll answer your question here in a second. What you do need is a tempering valve, which we sort of brought up. Somebody mentioned something about hot water. By code, when you have a solar hot water system, which does have the potential of overheating and scalding, you know, you can get water 180 degrees. You can get it to boil. You know, if you don't do it right. So there's what they call a tempering valve or a mixing valve. Same thing. It's about. Let me see what the price on that was. I do know the price on that. Let me see. It was. They probably start about $60 or $70, and they can go up to a little over 100. What that does is it automatically introduces a little cold water into the hot water stream, so you can't get scalded. And there's a knob on there. It'll range from well, there's different settings, but it'll range from say 110 to 160. So you can turn that on, turn that up or down to either encourage or discourage the flow of cold water coming in. In our case, that valve is here only because of code compliance. I want it to be visible. Maybe later I'll move it to here, but it's here. So essentially, what I'm doing is, I mean, I could be mixing cold water into what we don't want. We don't want cold water going into this tank, but I've turned that thing up so high that it's not going to happen. I'm sure the cold water should not.
You're saying that's a code requirement here?
Solar, yeah. For any solar system, you have to have a mixing valve.
At that point, before the secondary storage.
Right. Yeah.
So I've seen just, you know, these big tanks, the heat exchanger tank. I've seen some, and I know space heating is a whole different thing, but they were almost like those kids' pools that are kind of, they bulge out.
Yeah, a lot of water.
They got a hold a bunch, and you just start throwing coils of stuff.
Yeah.
Here's my coil to go to my radiant floor, and here's my coil to go to my baseboard heating over here. I mean, is there anything wrong with using a tank like that with this?
Well, just more expensive. Those tanks that you see, those big tubs, a lot of those are handmade, or they'll sell the tank itself, and you line it with an EPDM liner, and then you just start throwing coils in there, and that is exactly right. I mean, you can it works either way. It's just it would be extremely expensive to build a stainless steel or a big metal tank that size.
These are made out of plastic.
They are made of plastic, yeah. Yeah, they do.
They look pretty, I don't know how much they cost. I don't think they're all that much.
No, they're not. They're not.
You're talking, what were you talking about for this one here?
That's maybe $600-800 for that. Well, that's a stainless tank, so it's more than that.
Stainless. Okay.
That particular one that we have is stainless, so it is not $800. It's more. It's probably more than that. But most of them are glass lined, so they'll be in that range. But those big tanks, if you had to build a tank that size out of the materials that we build this size, it'd probably be well over $1,000. I mean, you know.
The key is to have it be insulated and sanitary reasonably, right?
Yeah, that's all. Yeah. But you know, as far as in a closed system, the sanitary part, you know, you're not going to.
Yeah, we're not touching anything with drinking, so to speak. Right. So, and I could put some algicide in it or something, because this is going to be hot, this big thing, right?
Yeah. Yeah.
Do you know a good hack where you could make your own heat transfer tank, like running copper through the middle? Or?
Yeah, that's what they do. And basically, like he said, in fact, even the commercial systems for space heating and some pool heatings and stuff, they have a tank, they have a plastic or a metal frame, just like this table, this roundness of this table. It's about up to here. It's a little bigger. It's up to here. They line it. This frame is strong. They line it with, they have a skin around it so it doesn't pop out. They line the whole thing with the EPDM. It's a very special, it's like the roof coating they use on industrial roofing. And they use it to line ponds with, so it's really tough. It's thick, it's about almost a quarter of an inch thick. And they line this whole thing so they make a big bathtub out of it. And then they just plop into their massive amounts of coil tubing, coiled copper. And that's...
But using an existing water tank, like I was thinking a gas one running like something in the middle.
That wouldn't be enough surface area to do it right. It has to be more surface area to make the heat transfer. Gas to water tank is not going to do it. It's not enough. That tube down the middle is not big enough to have a surface area that would be enough to make it work. Okay. Yeah. It'll work, but it won't work very well.
My other question was, it's going to be hottest when the sun is perpendicular to the panel.
Yeah.
Is there a way to, in the winter you need more heat than the summer, so what's the ideal angle?
Okay, I'm gonna do the solar siding because she reminded me we're about the middle. That went very quickly. Fortunately for us, the thermal, hot water PV panels are very critical about what the angle is and how they track. If the sun's coming down on it. In some climates, in colder climates, they actually have tracking, so it follows the sun, which is expensive, and it's problematic because it jams up with ice and all that stuff. With the solar hot water, it doesn't matter. I mean, it matters, it makes a difference, but the panels can be anywhere from totally flat to that much and not lose more than 15% of their total availability.
Something like this would be the best because when the sun's, you wouldn't have that scalding hot extreme because you can only take so many hot showers in the summer.
Yeah.
But then in the winter you'd be.
Well, you can't easily. I'm not saying it can't be done because there is high temperature industrial type tubing that you could probably do it with. These panels are almost always. I've never seen one. I'm sure somebody has made one that actually can move. In other words, in the winter you can reset it, and in the summer you drop it. But that's, like I said, that's not done.
You're probably having too much hot water in the summer, though.
Yeah,
and
right.
Not enough in the winter. So
Yeah.
could you just position it for the winter?
Yeah, that's one choice. In fact, what you do is you would ask the family, or if you had a certain situation where, like, if you need a lot more hot water in the winter time, we'll just set it for winter and leave it there. Yeah. What I've done is set it for the middle because Pat said.
Don't use that much efficiency anyway.
No, we use very little efficiency, and Pat said it really doesn't. He said we probably use more hot water in the summer, but even in the middle, he's going to have more than enough. So I didn't want to push it even further and have him lose it in the winter. And it really loses very, very little efficiency between, say, 25 degrees and 45 degrees. That's a good window in there. So that's set it at 35.
Before we leave this diagram with that controller, I'm assuming that controller can also be used to have, or do we need a pump to get it into the secondary system, or is that a circulation based on the
This one here? No, that's pressurized by the house water. Okay. House water pressure.
Is it moving because of the heat coming through?
No. It only moves when you turn the water on.
Okay, so I'm not really having any hot water over there unless I've got the water on.
Right, exactly. It's storing warm water, hot water, but it's not going to leave the pipe until you turn that faucet on. That's storing hot water. It's not going to leave until you turn the hot water on.
But by the same token, I'm not putting any hot water into my secondary tank.
No, you're pumping it all into this tank. Exactly, yeah.
Did you mention the name of the controller?
I think it's called Eagle Sun, that particular one, but that's a proprietary controller for this one company. It's just called a differential controller, and you can find one as long as it's for solar thermal, which is another word for solar hot water. You'd be fine. Let me see. Is everybody's questions answered as far as that diagram? Okay, because I want to.
This is basically a residential heating.
It's what?
It's basically a residential.
Residential heating, but yeah.
For a greenhouse.
For a greenhouse, you'd use a lot more panels and essentially more storage, but it wouldn't be a whole lot different. It'd just be more, more bigger. Yeah, more bigger. Yeah. Yeah. Now, okay, maybe I should. When you get the water for our greenhouses here, the water going through that system has to be 130 or higher. Maybe up to even 120, 130, and up to a little higher. You'll need higher temperatures to do forced air heating in a greenhouse, or hydroponic heating. That's a little lower temperature. I don't know which kind of heating. You're going to put it through the floor or blow it through fans.
The initial thought is to put it in barrels.
Okay, yeah.
Plastic barrels.
Yeah.
The blue ones.
Mm-hmm.
And interconnect those.
Right. Well, that would be a lower temperature. So, yeah. So it would be more like this system. You'd just be more of them. That's all. Yeah. So let's see. We've got everything's been answered. So we just what I wanted to do is take.
Are you going to talk a little bit more about the heating also?
What heating? What?
Heating with hot water.
Yeah. Let me just go through the siding and stuff first. And just ask me again so I don't forget. Heating. I'll just say it. Heating requires to blow air through a radiator with a fan, which is what we use, these hydronic unit heaters, they call them, the Molines. In the greenhouses, they'll have hot water comes in, a big fan, and there's a radiator in front of it. And when the fan turns on, it just sucks the hot air from that radiator and blows it out into the greenhouse. That requires a minimum of about 130 degree temperature water to make it, because below that, it just feels like cool air coming out.
Radiant heat, you usually
That's lower. That's 100. That's between 90 and 120 at the most, really, because it'll break down. You don't want that concrete will start to break down when it's buried over that, so you don't want it too hot. And then for other like baseboard heating, you really need temperatures up at 180 degrees, 170 for that.
Really?
Yeah, to make it work. I mean, it can work below that, but to make it give it 100% action through the coldest of the days in the winter.
And the tank size would be the same,
these temperatures are generally, we can keep them down at between 110 to 130 degrees.
No, I'm sorry. Like if you were doing radiant heat, could you use an 80?
Oh yeah. You could do that because you're feeding. Basically, what you're doing with the radiant floor heating is preheating the water, because you're always going to have a backup little boiler, a little munchkin or something to boost your heat. All you're doing is gaining efficiency by feeding it hot enough water, or it won't have to work as much because it's already hot.
Yes.
Yeah, that's all.
So you would use a boiler instead of a water heater for radiant heat?
Well, they're little boilers. Yeah, they're little flash boilers. They're just real little gizmos that they hang on the wall sometimes.
There's
Direct vent.
Conflicting information about that around. There's lots of reading and.
What would you use besides a boiler? Like a hot water heater? Well, you can, but the hot water heater wasn't designed to manufacture that much hot water at that flow rate. That's why that's not a good choice. Because electricity.
Hot water heaters are 4,500 watts.
Yeah, it's 45. Yeah, it's not. It wasn't made for that because it's constant. It's made to heat water and have it sit for a while, and then heat water a little bit. And it's like starting your car. You don't expect to sit there and crank the car for 8 hours.
The most popular thing used on radiant floor heat is like a Renai tankless water heater.
Yeah, a Munchkin.
Constant water flow. I mean, that'll pass your code.
What's that now?
A Renai or a LG constant water heater, a tankless water heater like you see on the house.
Tankless.
Mine hooked into the domestic hot water and for that had to be there for code.
Okay.
Because they won't accept a wood fire or a boiler or anything as a heat source in the house by code. So the easiest thing to do is put that Renai on that thing and then. But being it's a constant flow, it'll heat it up. Radiant floor heat, well, all our systems always run 85 degrees.
85 degrees.
Yeah, they're not.
It protects the pipe and it's 85 degrees on the floor, your house is pretty warm.
Yeah. And that's the other thing. It's like it's relativity. I mean, if you start, people always think, I want more. It just, the hotter you make water go through a pipe, the quicker it's going to escape. Not just where you want it, but also everywhere else. And so the efficiencies come in when you keep that temperature down as low as you can and still be comfortable. And 85, 90 degrees is real common for radiant floor heating. here. Now when you get up in Wisconsin and Minnesota, where all that stuff came from, first they'll run it a little higher. Yeah, right. Yeah. Well, I didn't really know until I went up there and I talked to a guy who did radiant floor installs, and I'd never seen anybody down here doing it. This was years ago, and he said, "Well, we've been using them for a while. It's just the way they do it." I think they use a combination of that and wood stoves, and that takes care of everything. Okay, the next thing we're going to do is set up the solar siting tool, and I'll show you how I did that. We'll talk a little bit about siting, and I want to just take a little brief break because I have to get some water and that kind of stuff. And then we'll just go out. I don't want to walk all the way up to the house because it'll take up too much time, but we can probably just go down the steps and we'll go out here and I can show you how the siting machine works. Okay, this is a solar site analytical tool. It's called the Solar Pathfinder, and it will establish whether it's worth your investment when you choose a site, if it's worth the investment you're going to put into the solar equipment. So you really need to know if your solar window or the sunlight availability at the site you choose is going to be enough to fulfill your needs in a solar application. This is a lot more effective or much more important when you have photovoltaic electric panels, but it's also useful for siting for solar hot water, and it's even useful for siting for gardens. Anything you need sunlight on, you need to know how long the sun's shining and if there's any blockage during the day, because you could have a tree, you could have good sunlight at 10 o'clock, 9, 10, 11, and then there's a tree in the way or a building or something, and then the sun gets past that and it's good, and then at 3 o'clock there's something else in the way. So you got to figure out whether it's worth it. I mean, I have good, bad. How much actual sun do I get through the whole day? And that's important. So this little device lets us know that. And basically what it is if you can see I'll just show you, everybody there. That arc describes from east to west what the sun path in the sky is going to look like. And the top of it is the summer, and the top lines are the summer, and the bottom lines are the winter. So I'm just going to walk around. You can sort of get an idea. See, it's just a curve, east, west, summer high, winter low. Can you see that? Okay. Yeah. See? You'll see it more when we get down there, but it's going to be hot, and I know people are going to be.
I don't get what's it doing.
Well, it's not doing anything right now at all. It's just the sun has to be on it for you to do it. It actually reflects off that globe, but that's just the pattern that it follows. You see how it makes a little map for us? Yeah, there it goes. See, it's just a little device. So what we're going to do is, oh, you want a shot up there? Okay. Let me aim. I want to aim it a little better so you get a better view of it. Okay. Can you point at what it does? Oh yeah, this is the east. This is the west. This is the summer path, and the lower mark is the winter path. Okay. Okay. Well, let's go down to the.
Can I ask you one question? Is there an optimal time or a minimal time of sun that you need?
Yeah. Well, it depends on where you live.
Hours, I guess.
The solar window, the standard solar window that everybody relies on is generally from about 9:30, 10 in the morning to 3 in the afternoon. Anything beyond 3 is bonus, and anything earlier, there's usually dew in the air, moisture in the air, dew. It's not that you're not going to get anything before 9, but it's just that it takes time for the sun to heat up and get the energy out and get all that air cleared out. So the solar window is generally 10 to 3, 9 to 3, something like that. And we're generally looking at some, depending on the season, of course, so you're looking at, and also depending on the location where you live. Asheville is different than Portland, Maine. Your hours of daily sunlight is going to be somewhere between 4.5 to maybe 6. And you don't think that. I mean, you think, well, gee, it's 10, 12 hours of light, but it's not just the light, it's the energy in the sun is really only there for about that amount, 5 hours or whatever, 5.5 hours. So we're out in the middle. You get down to Florida and down to definitely into the equator areas, and you have a lot more. If you get up into Maine and northern Minnesota and stuff, it's a lot less. So up there, like I said, they actually track. If they have electricity production, they often track the sun. It's that valuable to them. They'll actually pay to have the panel on a axis that moves, so it's always facing the sun. And it'll also be adjustable, so it's in the winter it's going to be up like higher, and then in the summer it's set back so it gets the sun. So, so that's basically it. But we, as I said before, we, even with a variance, losing the early morning, losing the afternoon, and not adjusting keeping the panel at one location in the middle, we don't lose that much energy, so it's still worth it. It's just the nature of the beast. The absorber surface on a solar water heater is a lot more lenient as to how easy it's going to absorb. As to an electric panel, it has to be really straight on for it to get optimal efficiency out of it. So, yeah.
True also that, well, PV panels have to have direct sunlight, no clouds or anything.
Right. Yeah.
But so with the thermal collectors,
they'll work in the clouds. Yeah, they'll work somewhat in the clouds. And in fact, with a PV collector, until fairly, well, not fairly recently, but at one point in the manufacture of solar panels, you could damage an electrical panel by shading it. You know, and partially shading it, because that's going to, half of it's going to say I'm working, the other half saying, you know, so what, you know, and it'd be shortage. Now they actually have diodes to prevent issues, yeah, like that. But the good thing about the thermal panels is we're really looking for heat, not radiant energy. So the or not it's electrical energy. So it's a cloudy day, an overcast day is still going to give you some heat. Yeah. Yeah, because and it doesn't care if it's half shaded and half sunny. It doesn't matter at all. It's not going to hurt it. So let's go down to where the sun is. Even though in fact it's nice now because the sun's not bright, it won't be so hot. Okay. Let's go over here. We're going to aim that way because that's the sun. That's where the sun is. Get a nice level surface. Now these things there's templates on here so that everybody can use it in South America, North America, Europe and all that, and whether we live in Minnesota or, I don't have them all with me, I just have this one, but these templates are based on the latitude of where we live. So in Florida, we're at 36 degrees north latitude, and so Florida is less than that. I don't know exactly what it is, but it might be 20 something, and then if we go up to Minnesota or whatever, it's 40 degrees. So these templates are sold in a range. This particular one is from 31 to 37 degrees latitude. So that's the one we want. And what we're going to do is, there's a little compass on here, as you saw when you looked at it, and it's going to point, south. We're going to make it point south. So, that's no good. First thing we do is level it, because that's going to affect, if it's cocked, it's going to affect the reading.
Does it have a level on
it? It has a level in there. There's a little ball. There's a little bubble right in the middle. And
remove the legs? Or?
No, not yet. I can almost. You see. It's really picky. Okay. So the bubble's set up right now. We're aimed right to south. Now there is another thing I'll mention. There's true south, I mean true north, well, south is opposite of north, so we're actually reading north, but the opposite end of that is the same, you know, is the exact opposite. So there's a difference between magnetic north and true north. The compass is going to read magnetic north, and so depending on where we are, and there are maps available on the NREL site or on the Geographic Survey, it actually has the United States with the magnetic lines, and there's, you know, I don't know how many, probably 100 of them across. You're familiar with it, but we are at about, we have a 6-degree declination here where we are. It'll vary from half a degree to almost, I think it's 12 even, depending on where you are. But the magnetic iron or whatever it is, the magnetic core in the North Pole that's making this compass work, changes in the continental United States depending on where you are within the state or what state you're in. So I just know that right now it's about a 6-degree difference. So this will say we're at true north, but our true north is actually 6 degrees cocked, and there's a negative and a positive. So you know, it depends on where you are. So you can, if I was doing an electric sighting for our PV panel, I'd be very particular to, the software will do this for you, by the way. This is connected to a software. The reading of this will be tied into a software, and that will allow you to adjust for the magnetic declination. So I'm just going to pick true south because at 6 degrees isn't going to make hardly any difference for our hot water needs. It doesn't matter. I mean, it really isn't going to do anything. So, and especially at our site where at 3 o'clock we have a big tree in the way that we're not going to cut. We may trim it, but I doubt if we're even going to do that. We'll just leave it. If it was electric, we'd look at that and say, you know, that may be an issue, and we may have to move these panels over a little bit and get out of that tree. But we wanted them on the roof, and we wanted to keep the tree, so you know, it's fine. The other thing is with any of the panels, collectors or panels, if you have a situation where a tree you really don't want to cut or a structure you don't want to move is there, you can always just put a second or third or fourth collector or panel in there. You know, essentially that house could have been probably the house we're going to see up there with the installation probably could have got by with just one panel, but we wanted to experiment a little bit with some more additional storage and more heat into it, so we got 2. So that's another way of resolving the issue if you don't have to cut a tree. So anyway, I zeroed the level. I've got it directly pointed at north. So I'm interested in south, and we're going to plop the cap on there. And now, now the sun's coming out. It's hard to see, but you're actually looking at the reflection of it, but you can see the tree line. You're gonna see interruptions from the people here too, a little bit, but it's, you know, it's okay. You can probably catch him. But you can actually see it's a sort of a reverse image. You can see that, I'm going to step out of the way because I want people to see it. You can see the tree line, where the impact of that tree is, and so, you know, essentially you can see it's actually, the solar window in our case has a, you know, a bump, and then it's okay over here.
So does this record in any way?
Well, what we do is we take a digital picture. See, in the old days, before they had digital cameras, don't trip on that. I don't mean to say, I don't care if you step on it, but you're going to fall. That's what I'm worried about. Let me just move that. What we do is we stand directly over this thing, and it's a little bit of a trick because you really don't want your own self in there, but like when the sun's like this, it's not the ideal situation. You want a sort of an overcast day, but you sit over there with a camera, and you aim it as square as you can get it, and still catch the blue, a complete blue ring, and you can do that, you know, and then you take your picture, and then what you do is you download it, well, from the camera into your software, and then it will analyze that picture and do everything for you.
You could do this at any time of the day?
Yeah, I mean, it wouldn't, at night it's not going to work.
The reason for that is because it's seeing everything.
Yeah, it's seeing everything no matter what time it is.
Properly oriented,
yeah.
So it doesn't matter.
Doesn't matter. I mean, it has to have some light available to make it work. So I would do it between, say, 7 in the morning and you know, 7 in the evening. In the old days, before they had digital cameras, what we do is they give you, well, they still do, they give you 5 or 6 of these papers, and you can order more for nothing, you know, very cheap. and they give you a wax crayon, and then you can draw. I'm not going to do it because you mess it up, but you can draw on there, carefully look on there, and draw the outline. And then you take that piece of paper into the house, and you can then use these numbers, 5, 6, 7, 8, 9, 10, and these numbers, and every hour you add up the total, and then you've got a total window of how many hours of sunlight you got. The software is so much easier, but you can do it the old-fashioned way too.
Can I get a dead-on digital photograph?
Sure. Just hold it up there.
And what's that called, Richard?
Solar Pathfinder.
What did you say?
There's
I'm not seeing it very great.
probably about 4 different. It's hard to. It's not. You are seeing it. You just don't know it.
I like it. Doesn't it work better when it's not so sunny?
Yes, it works much better when it's overcast. And I can't help it. The cloud, was sort of good. But there's about 4 manufacturers, Diane, that make these kind of things. But the Solar Pathfinder is probably the most popular, and it costs about $299. You can rent one. They don't rent it. They themselves don't rent it, but there is a nonprofit that rents them, and you can look at it. You can just put rental Solar Pathfinder.
A nonprofit what?
There is a nonprofit that rents these, so you can rent it for a day and then give it back to them. Rents the tool.
You would send away for it?
They'll mail it to you. Yeah, they mail it to you, then you return it. Oh, this is ours.
I was going to say.
It's already ours. We don't need to rent it.
Oh, okay.
I mean, to rent out to people.
Oh, yeah. Well, the other thing you could do is, I don't know if everybody will do it, but you can buy a solar site survey. You can just call up a solar installer and say, I don't want to go any further. I just want you to come out, do me a site survey, and give me the report, and they'll do it. Yeah, that's the easiest way to do it because they know how. They'll print you. They'll do it. You don't have to fool with it.
Yeah. And the months are up there. Because you're only going to use this once. The months are.
Yeah. Well, no, we're going to use it in our case. Well, yeah, but what if you have a garden? You might want to do it for your garden. You might want to do it for a neighbor. I mean, yeah. But yeah, normally you don't use it once.
To figure out which trees you need to cut?
Yeah.
Or
If you have a site for a garden, you don't know whether that tree is going to get in the way of. If you want a garden back there, you're going to have to do it there.
Or your neighbor's hedge?
Yeah.
When is it going to be too high?
Well, we talked about that. And he said, oh, yeah, well, sorry. He didn't seem to mind.
No, I know. But
Yeah, no,
that
exactly.
would be a tool.
Yeah, exactly. And you know the growth rate. You can go find from a silviculturist. You can find the deciduous growth rate. Calculate that in the next 11 years. It's going to be your solar's going to be dead.
Right.
But the tree might be dead too. So. Okay, I think we've been out in the sun enough. So I'm going to pack up. Oh yeah, did you? It's really just. It's. Let me see if I can. See the outline. No, I'm just getting too much of a reflection. I'm getting the clouds now. See there?
Okay, yeah.
But over here, that dark mass right in there is the tree.
Okay.
Yeah, okay. All right. Are you finished? Okay.
Add more wire as you go.
Now that is going to tell us, going to give us the information for what we need to know. Here's a picture. I don't have this on the screen. I'm sorry, but the. No, that's not a very good picture, so I'm not going to bother. So what we're doing is getting information from the software. You load the software onto the machine. I might be able to bring it up. Let me see. You key in a lot of information. For example, for this house here, I got on the roof. And fortunately, it's not that steep a roof. It's only maybe 3 and 12 pitch, so I can walk on it easily. And I wanted to see, obviously I'm looking for direct south exposure, which it has. And unfortunately, the roof is opposite. In other words, in most cases, ideally, there's your roof. You want the sun to be on one of the. You want the sun facing one of the roof sections that way. We had to do it the other way. If my head is the sun, it's like this. So we actually had to mount it up like this, and they're cocked. But that's good for drainage. That's another reason that the drain back system works so well.
Because it goes down to one corner.
Yeah, it goes down to one corner naturally because they're tilted up and they're tilted, they're cocked, so it has to go down to that one corner. But there's other things going on. I mean, did I want it up front, really close to the edge? Did I want it back as far as I could get it back? And that particular house has 2 levels. There's the main house, and there's a garage and a little workroom, and that's at a slightly different level than the other one. So, you know, I couldn't mount it at the cusp between those 2. So so we also had, you know, did I want the neighbor to see if I put the panels all the way forward? It would be a little unsightly. So maybe I should. How much will I lose by pulling those panels back? So in the comfort of your office, you can sit there and play with all these things. You can take a reading. You have to take the reading. You take the reading up front, take the reading in the back, go on the west side, go on the east side, aim it around a couple different ways, and then you just take it all back and plug in your various factors, and it will tell you how efficient, how much savings you're going to get, all this stuff. So I can show you what we did here.
So where did you get the tilt angles? Was that just from some chart based on the latitude?
Well, yeah. That when you go to the, I'm just going to use the NREL site. I mentioned that before. National Renewable Energy Laboratories. It's a federally funded site that does a lot of work in. It's a research group, scientists that do a lot of work in solar energy and renewables, and they have. That's only one of many places you can just get the what the latitude is of Asheville, North Carolina. Right. And actually, it's even more specific than that. It's Asheville Regional Airport, elevation 2139. So everything, and that's the latitude and longitude. Oh, what the heck? Oh, okay. That's the latitude and longitude of the site. And the airport's only 2 miles from here, so it's perfect.
And since you told it was fixed angle, it said, well, then you ought to put these at this, or a fixed array, right?
Yeah,
It gave you those angles based on the latitude and longitude.
Yeah, the ideal tilt angle is 36, because I said that. 35.43 is actually what it is based on these parameters. So, and it's not, for this solar thermal, it's not that critical. Right. I could go, I did it from, where it says skylight position, I chose to get back so the neighbor, one of the reasons is so the neighbor doesn't have to look at the whole panel. He may be able to see, and I'm not even sure if you can see that, but it's also between 2 skylights, and that was another thing. I couldn't put it on a skylight. There's piping that has to go down, so I had to get either in front of the skylights or between the skylights, or move it completely onto the other part of the house, in which case I'd have real plumbing issues. That's the most important thing, is you have to be able to drop that plumbing cleanly into the tanks below. So what do you have to go through to get there? In his case, he has just an attic storage with no insulation, nothing in the way. So we just put it on the roof right over there, dropped it straight down through the attic, and then directly below that was a workshop, which is not even, it's tempered, but it's not heated. And that's where I put the solar storage tank. So it was a pretty clean drop. I mean, there's a little bend, but it's not that bad. So that's the other very important thing to think about. How are you going to get that plumbing to drain? It has to always drain. Pumping, it doesn't matter, but the drain side, I mean, well, both of them have to, because it'll drain from, it can drain from both sides. So it has to always be on a downward slope. So we picked the tilt angle at 36, but I also ran the numbers at 25, figuring, then the neighbor can't see anything. 25 and all the way up to 45. 45 would be really good for the winter, but it would be less effective in the summer. So 36 is perfect because it's set at, it'll be perfect for the solar, it'll be 2 times a year perfect. It'll be solar equinox, spring and autumnal equinox. And then in the winter it's still going to get plenty, in the summer it's going to get plenty. So, that's why usually setting it at your latitude is going to be, a good choice. Yeah.
Do you know what pitch roof that is, the 36 degrees?
3 and 1?
What pitch of a roof that is?
36 would be? 412? No, it would be around there, yeah, but it would probably be more like a 512, but I'd have to, do the calculation on it. So in other words, if you had a roof that was already there, then that's what they want you to do. I mean, when you talk to the people that sell you this stuff, they really would like you to do a very aesthetic installation because it makes them look better too. They're trying to promote the idea of these panels. They don't want something ugly out there. And I told them it's a farm. There's, it's not a subdivision, so it doesn't really matter. But when you have a subdivision or a place where there's a property owners association, those panels are usually mounted right flat onto the roof, and they look like a skylight. That's why they make them that way. The azimuth is the degrees off of south, and we're at 180. We're right on the button. That would only change if something was in the way, if it was beneficial for me to shift it to the west a little bit. If you're going to shift it anywhere off of that, it'll perform better on the western side than it will on the eastern side. And the reason for that is on the eastern side, it takes a while for the sun and the air and everything to clear up. By the afternoon on the western side, all that's already done, and you're getting that full western sun heat and energy afternoon. So it's always better to go on the western side if you have to do that. So let's see what else is here. The collector area. Let's see, skylight position was the one I chose. I just called it skylight position because it was over the skylights. It's not over them, it's between them, actually. It's only over one small one. The declination is that magnetic thing I was talking about, minus 6 degrees. It's a thermal report, because if we were doing a photovoltaic one, it would be a PV report. It's a fixed angle. I'm not changing anything. I'm not tracking it. It's got 35. We talked about that, 35.43 degrees straight south. We've got a full window between 10 a.m. and 3 p.m. every month of the year. So we're just feeding it this information to digest and tell us what's going on. The collector model is AE32. They already have it built in. They already know in the software the efficiencies of every panel manufactured. So when you tell it, I'm using an AE32, it pulls its numbers up, and so it knows what to read. The collector area is 31.9 square feet. I'm using 2 collectors. So the total collector area is 63.7. The solar fraction, that's the calculated percentage of total hot water that this system will provide. So in other words, we're not going to get 100%. That number is not 100. It's 0.72. 72.3% of the water will be solar heated throughout the year. That figure is 12 months. If we were just to read July, that figure would probably be 95 or 100. Yeah.
And that's based on the residents' usage of water?
It's based on the what?
Residents' usage of water?
Well, that's the other thing. I plugged in a 40-gallon per day usage, which was about as low as I could go, and still, because I have to calculate the fact that there may be other people, people being there, interns, Mira, whoever, people taking, maybe four or 6 people taking showers. So I had to, and plus he said, I'd really like to run maybe see if we can do a space heater in one of the rooms. So, I had to build up a little more, I had to just sort of estimate. So yes, that's important though. If you know you're going to use a lot more, some families go through, 70, 80 gallons of water per person per day, hot water. I mean, it's hard to believe, but they can do it. Then you change that number, and that solar fraction would then drop. Then we get down to how many BTUs over the total year, we're going to get 8.5 million BTUs from this system. The electricity saved is 2,511 kilowatt hours. So our annual savings, I plugged in the cost of 12.6. The residential cost of electricity in this area here is 12.6 cents per kilowatt hour. So I plugged that in first, and it tells me we're going to save $326.55 over not having the solar system, based on our normal 4,500 watt electric water heater, which I also plugged in. So see, if I were to go through all this plug-in stuff, and it's very simple. It would take us, it would be an hour. So I don't want to go through it. I'm just telling you what I did. And there's a good picture of our tree, of our window. See, we were here, which is a different site, but we're actually this is actually up there. So in the process, after I took the picture, it gives us an image of the whole thing, and it's much more clear in the digital camera. It's much more clear.
It looks like it's really shading quite a bit.
Well, the black is the useful part.
Oh, useful.
Yeah, the black is useful. The gray is the shading. It's just backwards. Yeah. So what I did was with the software you can actually draw a digital line. You have a map. You have that map out there, and you look at the trees and all that junk, and you draw a digital line from point to point, and you describe, and no cheating. You describe what it actually really is. You're tempted to say, well, that little branch, that's not going to make anything. But you really need to be accurate, and you describe every single place where a tree is impinging on you. Like here, where it dips down there, that's a tree in the way. All that on this side is on the complete western face. The tree is totally blocking everything after 3 o'clock. So I just blacked it out. Now there is another function in here where you can choose the tree, and so if it's a pine tree, it's going to stay like that, but a deciduous tree is going to lose its leaves, so that factors in at what are you going to lose. They give you a choice. Are you going to have 40% availability, 60, 50, whatever. So, because when it drops the leaves, in the winter, when it drops the leaves, it's not like it's disappeared. It's just, you still have the branches and the trunk and everything, so you have to have some blockage. But it's going to be a lot less than a full summertime bloom. So it does all that for you.
Well, now I'm definitely calling you.
So we drew the picture, and that's our window. All that is good. So now it knows, okay, this is what's available, and it does the whole printout. So I've got, let me see if I can get to the summary.
And if you do multiple sites, it uses that as a whole, all your multiple sites to be able.
Well, it only does one site at a time.
Oh, okay.
I don't really know how you're going to do. I mean, there is a way of factoring it in there, but you have, like, if you had how would you?
Multiple.
Oh, you mean you said I'm not really sure where I'm going to put it?
Yes.
Yeah, you just it's one site at a time. So you look at the one site. If site A was 68% solar fraction, then you'd say, would I be willing to cut this big branch off that tree and make site A 78%? Or would I be better off moving it to site B where I have a 72% fraction? I don't have to touch anything. And you have to sort of think about that. And in solar thermal, yes, that would definitely be worth it rather than cutting trees. Yeah.
Just in terms of component costs of that system that you put in there, and the payback that you had of what, 360 was it?
326 of hot water use.
326. What would be the payback in terms of years running?
Of the system, that would probably be it's a pretty long. Let me see, it would probably be pushing over 10 years. 10. Sometimes these things can go up to even 15 on the water. Now the PVs can be shorter because the price of panels have come down so much. But the other part of this is that that's only a 40. That's because his water use is really low. We put in a bigger system than he really needs. If I was to bump, let me put it this way. I guess if I was to bump up the water usage to a more realistic thing as to what I thought.
You would have only needed one collector.
Yeah, that's another way of putting it. We really don't need 2 collectors. I could probably get it by with 1 collector, and that 10-year factor would have come down to probably closer to 7 years or something like that. That's a better way of looking at it. So I had to sort of fudge things a little bit because I was told that we have other people coming and using the showers, and we also want to use some of that hot water for heating. Maybe, we're going to experiment with that. So, and this is basically, I know you can't read it, but this is basically a month by month, no, I can't read it either, a month by month analysis of things like the unshaded percentage of the site, 69 to, let's see, the lowest is 60%, and then the highest is probably going to be, let me see, we get 60 to 69%. How much solar radiation is available in what months, site efficiency for each month, ideal site efficiency, total solar resource. All this information is available to you. Like if you had a customer, essentially here I work here, so it's not like, but I still have to be conscious of, we don't want to spend money we don't have to spend. But if you had a customer that's really trying to nickel and dime everything and really you're trying to convince them to buy this system, you're going to have to analyze all these things and let them know, you're saving this much, and in the winter, say, if you want me to adjust it for more summer use, we'll do that, and we'll get more savings, that kind of thing. So that's basically what we're looking at. So I don't think. Let me see if there's any picture layout. That's just gives you an idea. See how much clearer it is in the picture? The tree in question is in the afternoon up here. That's me. That's me with the camera. So that's not, that's, when I, see, if I had a scanner to read that and tell me how to draw those lines, it would read me as a problem. So that's why I go in, and I know that's me. So I just avoid myself and track, you know, I make my point from there to, you know, I go around here like this, and then I'm not even sure I counted that. I think I just...
trees too?
No, that's a tree. Right here is a tree. These are trees. That's me. So I just drew the line accordingly. And then I told the software not to count me in the picture, you know. So that gives you an idea. We have perfectly south. We have me, my shoes, and all that, and I'm standing with the camera. So that's it's a pretty good idea. And what ended up was that, because I drew a straight up, you know, I just drew a straight line up, followed the lines, and then drew a straight line down.
Do you have the fudge factor for daylight savings time?
No, it's just they figured into the software, but you're not really losing time. You're shifting hours. I mean, it's not, you know, you're not losing sunlight. Okay, so let me see what else we have on here. See if there's anything. Yeah, I just did a 40 gallon usage, which I could have done. You know, he didn't really know what to say when I asked him, but some people sometimes say, yeah, I know. We got all our kids are soccer players, so in the summer we have a lot of usage of hot water. In the winter, everybody's lazy and nobody takes a shower, so you know that's a lot less. So you know, I could plug in every month, but I just left it at 40 just to make it easier. Tank temperature 135 degrees, which is higher than normal, but higher than the real situation. But I knew that we may want to use some of that for heating purposes. Water supply temperature was 60 degrees, which actually it's more like 64, but I just used 60 because you know, I wasn't sure in the winter what it was going to do, so I gave it a little benefit of the doubt. Main tank, the storage tank is 80 gallons, the main tank, and the secondary tank, which is the hot water heater in the house, is 50, so we have 130 gallons of storage. So that's basically, you know, all that. And then the savings, that's at 13. I don't know why I did that. It's supposed to be 12.6. We already saw that before. So the annual savings is $326 a year. And that's all estimated, yeah.
So could we talk just a little bit more about this system that you've designed, and I'm very interested in that, but also using it for, let's say, baseboard hot water.
Okay, I can do that now.
How would we put that, and I also want to use it for domestic hot water, so what would I be looking at here?
Okay, well,
changes to the...
Yeah, I'll do it. I do have to be conscious of time. Okay, it's 4:10. To do baseboard heating, you need to have water, as I said, between 160 and 180 degrees. You have to use special oxygen barrier PEX pipe. You have to have a backup gas furnace. They have electric ones, but they usually use gas or propane. And you can use solar, but to get 180 degree water, it's just, it's a lot of panels and constantly. And so basically what you're doing is addressing a situation of preheating the water, not relying on the solar to handle the whole. It would cost a lot of money to make solar handle the whole thing. And then at night, when you really needed the heat in the winter, it's going to be sucking upon a system. That 180 is going to disappear. Yeah, there's no regeneration. So you're going to be drawing on, because you really can't store water very efficiently at 210 degrees. So you're going to draw very quickly. You'd be drawing that. If you stored water at 210 degrees, you'd be drawing it down to below 180 pretty quickly. So it's really not a good functional thing other than preheating your boiler or your Rinnai, whatever you're going to use. So that's see, normally in a radiant floor system, temperatures are much lower, so you can use a smaller backup heating system. But in a baseboard heating system, you have to have basically a boiler even a small boiler, but it's still a boiler.
The baseboard uses convection.
Yes.
Which is why you need the high
Right, it has to be a higher
versus
temperature.
the floor. So
Yeah.
if you had the choice, you would want to go with radiant floor and
Yeah.
not a baseboard heat.
Right.
Exactly.
If you wanted to use.
The radiant system actually, the whole room turns into a big circuit of air. It sucks the cooler air through the radiator fins, the baseboard fins, and then pushes it up, and it's all a big self.
You need that high temperature.
Yeah, you need the high temperature, right, to generate the circuit, the actual movement of the air. Very quiet though. I've got it. It's very quiet.
Oh, it's very valuable, thank you. I think what you're saying is use a radiant floor if you've got it.
Oh, definitely, yeah. If that was your main question, yes. The radiant floor is a lot lower temperature, and you can use the solar to feed it.
And it uses a thermal mass, I'm sure, also.
And it has the thermal mass of the storage, so you don't have it doesn't lose its heat that you fed into it. Yeah, the baseboard heating has absolutely no storage at all. Yeah.
I might have missed this earlier, but can you run a radiant floor system and a hot water usage system from one?
Yeah, you can do that, but you have to. A radiant floor system is the temperature the temperatures are close enough that you can do that, but you may have to. You may have. Well, yeah, you may. The thing is, you may have to temper the water. By tempering the water, you're sort of defeating the purpose. But if you need to lower the temperature for the radiant floor heating, that's one way of doing it. Is actually adding a little cold water to make it, to bring it down. You can also possibly pipe off some return water that's already cooler and use that. You see, there's ways of sort of managing the system that you can actually do.
Could you set your system at 110?
Yeah, you could do that, and then you're.
I'm thinking of a space that would just hold all this equipment that has to be.
Yeah, and if you were to say the primary reason for your solar system is to do a radiant floor heating, and then the domestic hot water is an add-on, then you're just saying, okay, well, once in a while then, because my water isn't as hot, once in a while the element is going to come on to back me up, and that's fine, because what I'm really getting is heat out of the floor, which is what I want. So that's the way. But to answer your question before, because I didn't, splitting the system, if you had a baseboard high temperature system and then trying to borrow some of that for domestic hot water is not going to work very well, because you'd have to mix cold water with it, and it's just adding, that's just stealing what you just built all that energy up for. So, okay. Is there any other questions like that as far as? Yeah.
Well, so what would be the best? Is there a way to use an electric backup?
Well, that's basically what.
For radiant heat.
For radiant heat, yeah, they do it, but I think the gas is is almost always more. Gas is more. That's a discussion I did. In fact, I have to talk about that too. Anyway, I should have done it in the beginning. Electricity is 100% at the point of use. It's 100% efficient because that element heats and it is no waste or anything. But to get the power from the coal that we're using to make the electricity, by the time it gets to that element that you're using, we have lost 60, 70% of all the energy in that system. It's lost through the generation, it's lost through the mining, through the coal processing, it's lost through the wires, it's lost through the transformers, it's lost through everything. By the time you get it to your house, you've lost a tremendous amount of energy, and it's extremely dirty. Coal is an extremely dirty way, even though they've cleaned up the stacks but just the mining of the coal and the water it takes, I mean, the whole thing is just a very bad way of making power.
That's a good argument for electric cars. They are not.
Yeah, well, yeah, that's the other thing. Is if everybody bought an electric car, we wouldn't have enough, nobody be able to turn the lights on because they'd all suck the. Yeah, yeah. Well, I mean, the thing is, electric cars were also meant to be solar charged too, and all that. But that's a good point. So what we're saying is that natural gas is actually a primary. It's a direct use of you've got gas and it burns, so you're using it right there. So it's more. It's not quite as efficient, but it's actually more. It burns cleaner, and.
Even if you made your own electricity with PV panels.
No, that would be different, but it would cost you a whole lot. Yeah, you'd have to make a lot. Yeah, you could do it. That's a lot better, but it would cost you a lot of money to buy those panels to do that much. Because heating with resistance heating with solar panels requires a lot of panels.
It is not practical.
It's not practical. Yeah, yeah. So now the other thing I should say, because as hydraulic fracturing comes into play and all that, you know, 5 years ago, I mean, even though fracking existed 5 years ago, say 5 years ago, I was pretty safe in saying natural gas is really a good choice because it burns clean and it's still pretty efficient. The furnace can still be, my boiler, my propane boiler is 89.7% efficient, which is, you know, I could spend another $1,000 and make it 90% efficient. Is it worth it? No. So, you know, that's a pretty good efficiency. But now, if we're looking to the future as gas sourced from a hydraulic fracturing operation, you know, natural gas doesn't look so good anymore. If we're going to taint our water just to get more gas, that's not really the best choice. So, you know, it's not just a political question. It's also a very economic question, and
It would be worth to put in a system for radiant heat without a backup.
Right.
And have wood or something.
Yeah. Yeah, you can use our boiler. I don't know if you can see it from, you probably can't because it's in the corner. But those greenhouses, as a backup, have wood-fired boilers. You just chuck wood in the boiler and it pumps the hot water through heating units, through fan-driven forced air heating units to heat the air in the greenhouse. So that's like if, you know, if the sun, in the wintertime especially, at night when the temperature drops down, we have to have some heat in there. That thing just kicks, you know, can kick on. And, yeah. Yeah.
Anyway,
Yeah, that'll hold it.
Well, the thermal mass.
Yeah, right.
For passive solar.
Right.
So
it's going to be there, yeah.
Radiant
Yeah, I got it. Yeah, that's exactly right. You got to kill two birds with one stone. Yeah.
With the greenhouse, you could almost do hot water, wood-fired hot water and piping in the dirt. I mean,
We do have that, and the other at Grandview, that's what we do have.
And you have a tie-in with a solar.
It's not solar. It's a biochar operation where they pyrolyze wood and make a fertilizer, an organic fertilizer.
Yeah.
Okay.
But I wonder if there would be like I have a wood-burning stove that has a loop.
Yeah, loop. Yeah. Yeah.
And then it goes out to another room that I'm gonna have my solar thermal. And I just wonder how, you know, that would work together. You have the wood stove going through PEX, comes out, pops out at the water heater.
Yeah.
That's gonna have a
Yeah.
loop.
Right. Yeah, I mean, it'll work. Anything can add to it. It really, in a question like that, other than safety, I wouldn't start the PEX till I get well away from the wood stove. But you know, that's fine. So, and think about steam and boiling. You have to have temperature pressure valves close to the wood stove because it could airlock, and then you'd have an explosive situation in the tubes in the stove.
I actually did a copper
Yeah.
run.
Right.
Maybe not as long as maybe you might have
Yeah.
suggested, maybe 4 feet.
Yeah.
And then I put a valve there.
Right.
So if I ever turn off the circulation thing, I make sure.
Yeah, it's off. Yeah.
And its steam comes out.
Right. Yeah. So you got that. Yeah. But I mean, the code, you know, from the issue, and I know the code doesn't matter. You already have the house and all that. But I mean, when they write these codes, they think, well, human error is very possible. So they want something that's automatically safe. So that's all. But the only other, besides safety, the only other consideration you're going to have is economics. Is it worth it to put this much money into, you know, whatever you want to accomplish to add this much heat? You have to sort of balance your heat against what it's going to cost to get you that heat in building your little additional heat thing. That's all it amounts to, really, and your time. You know, and for people like us at the time, it's just fun. You know, you do it anyway, so that's good. But okay, so that's the software. So that lets me know that you know, that we're going to get basically this much money or this much hot water provided to us by the collectors. What I'm going to do is see if I can pull up the SRCC site. I'm going to unplug this so you don't have to look at all this. And let me get over here. I'm going to give you these handouts because it was... Yeah, maybe you can just pass them around to everybody. Let me get this out. While I get a drink of water, I'm dying here. No.
What does SRCC stand for?
Solar Rating Certification Corporation. I had nothing to do with that.
Did you bring that here with you?
I'm happy to say I haven't done any legal work in the 2 months That's why I'm smiling right now, I think.
But you have some cards you want to hand out.
I call. If needed. I'm happier in the garden.
Okay. That, what I handed out there is not, do you have an extra one for me? Yeah. Okay, just put it on top of that. Thank you. Okay, so just going to the, I'll just walk you through this because it's a pretty interesting site. This company, the Solar Rating and Certification Corporation, is the UL of solar thermal panels. So if you want to sell a panel in the U.S. and actually sell it successfully, you're going to have to get it rated. Not that you can't sell them without the label and the certification, but you can. You're going to be much more authentic and reliable, believed, if you have the rating, the testing done. And as I said, there's hundreds. I'll probably end up showing you here. So basically, there's a lot of stuff about us and all this stuff. But here's what we want: the certification and listing. So here is the rating and listing directory. All the manufacturers have submitted their panels for the testing facility, which is in it's connected with the University of Southern Florida, I think. So their Cocoa Beach facility is one place, and I think they have a big office up in Washington, D.C. So we can talk about, it's not just solar residential thermal, there's all sorts of industrial solar heating, pool heating. We have evacuated tube panels, we have standard flat plate panels, we have collectors that are based on different technology, which is mainly used in industrial situations. So they've got a lot of stuff. So we're not going to go through all that stuff, but what we're going to do is go through the solar thermal collectors, which is what we're talking about. Flat plate, tubular, that's integrated system, thermosiphon, concentrating. Concentrating is, they don't use them so much anymore, but they do use them in industrial situations where they actually have a mirrored surface, and then they have a tube running. It's like a big trough, and it's actually this big, and then there's a central tube down the middle which they put water on, and all that sun, the inside of that trough is a highly reflective surface, and they bounce the sun off and aim it and concentrate it directly onto that tube. It gets really hot, and then they pass water through it fast enough. Even though it's boiling hot, the water is boiling hot, but even though the surface of that pipe is extremely hot, they pass water through it fast enough to draw heat before it boils. So that's a different type of collector. We don't use that in residential. So we click on that. And then we're going to have to ask a few questions. So you want, I know what we got. It's going to ask you a couple things so they can, Oh, by the way, just to give you an idea, like how many manufacturers are there? I mean, look at this. So there you go. But check it out. Okay, you got Jiangsu, you got Xenon, you got Jiangxi, you got Hulex. That's I don't think that's foreign. You've got, even though some of them have English names, they're made overseas. You've got Baymak Makina. It sounds like it's possibly a Russian collector. You've got Steibel, which is German. You've got a whole bunch of them. I see a Greek one there. As I said, there's a couple of places that make good collectors that are in the Mediterranean region, because if you've ever been there, I was in Israel for a while studying some of this stuff, and they have looking out from the hotel, you can see all the little 3- and 4-story walk-ups. Almost every roof has hot water collectors in them.
In the U.S.,
yeah.
Hot water is made by solar primarily.
Yeah.
It's not electric, because they don't
yeah.
have the electricity.
They don't have the grid. They don't have the resources. Yeah.
Some days they don't have electricity.
No. Right.
They only get electricity for 4 days of the week.
Right. Right. They actually.
Their hot water.
Yeah. They hoard it. But anyway, we got to plug in some stuff here. So we know we have it. We look on this list, and we have a. Fortunately, it begins with an A, so I don't have to go down the whole thing. Alternative Energy Technologies. So we click on that. So that's one pick. Brand name. They make something called the I forget what the name of it is, but I happen to know that the one I want is alternative energy. They make two lines. One is a more commercial line, and one is a residential line. So we have the residential line, which is just the alternate energy line. The other one's called like Eagle or something like that. We want the request type. It's a glazed flat plate. It's not a concentrating or any other thing. It's a glazed flat plate collector. The fluid is going to be liquid, because they also test space heating with air going through them and other stuff. The unit, I'm just going to say US units to make it easier. And then we're going to search that. Those parameters bring up oh, here's the whole list. Yeah, here we go. That's what I was looking for. You're right. I have the AE 32 square feet. And then all the information's up here to double check the AE 32 and when it was tested and all that stuff. Now this is sort of complicated, and it's really not. I'm not going to go into the full explanation. I'll just show you where you need to be on this. It's also sort of small, but I'm showing you this so you can go, if you want to go home and look at it and study it, you can see it. The other thing too, I just want to point out, and I'll mention this again. This book, if you want to buy a book on solar energy, solar hot water, that's about the easiest to read, and I think it's only $25. This is the second edition. It's been around since 2009, I think, maybe even earlier. But it's it's very readable, very accurate on all different types of solar hot water systems. It'll have an explanation of basically how to read that chart, but we don't need to know that much detail. What?
Who wrote the book?
Oh, who wrote the book? Who's it by? Okay, I'm sorry. Bob Ramlow and this other.
Didn't you write a book yet?
I did write a book, but it's on fuel, not on this. And the reason other people haven't written too much on it because he did such a good job. Now there are some academic texts and there's definitely some engineering texts, but they're mostly for industrial applications where they need like massive amounts of hot water and how to balance those systems and everything. And I know you really can't see this that clearly, but the point is that any one collector is usually used for a whole bunch of different applications. So it's not just residential. It could be used for many different things. So you're also going to use it in different places. So whether it's going to be Maine or Arizona or whatever. So or for pool, not just residential heating, but pool heating or other stuff. So what we're looking at basically is this. Can you do what? Yeah, you can zoom it up. Just on that first. Yeah, there you go. Okay, that's great. Thanks. Some of the parameters we're looking at is we're not going to worry about kilowatt hours because we're looking at thousands of BTU per panel per day. So we're looking at high radiation, medium radiation, and low radiation, and that basically is bright, bright sunny days a lot. Like if you live in a place where you have, it's like almost always, and you can find this out from the weather station, percentage of cloudiness in your climate, and it'll say, 70% sunlight, or 30% cloudiness, but here it'd be less than that. In other places it'd be a lot more than that. Like in Massachusetts, northern Massachusetts, they have a lot of clouds. So basically, the high radiation is places that like Arizona. The low radiation would be places like Minnesota and Massachusetts and maybe inland Maine and other things. So most places, and including us, is going to be medium radiation. So that's sort of one parameter you want to use in your selection. All this is aiming towards which solar collector you want. Is the AE32 a good choice for you? So what you're going to need to know is, using that sheet I gave you, you're first trying to figure out how much hot water you use, then you're trying to figure out whether that collector you're choosing is going to be the right one for the amount of hot water you need for your house. So we're make matters easy on ourselves. We're going to say it's medium radiation, so that's all we have to say here. And this is a little more confusing. This is basically T1 Ti minus Ta, which is temperature, inlet temperature minus ambient temperature, which is the temperature of the water at the inlet as opposed to the temperature of water at the ambient temperature. So the different categories A through E reflect what that difference is: -5, 5 degrees, 20 degrees, 50 degrees. So we have water coming in. We have a differential of say 60-degree water coming in, and then when it leaves at the surrounding area in the collector there, it's going to be maybe 110. So you've got a differential there of about 50 degrees. So for our purposes, without even worrying about any of this other stuff, we're going to be mostly looking at the C or D category. More shifting into the D than the C, but it's going to be, so we don't have to sit here for hours and try to figure out exactly where we need to be. If we were engineering something, yes, we would do that. But for just our purposes, we're going to look at medium radiation and somewhere in between C and D here. You can pick D or you can pick C, but you're going to be in the ballpark. So then we know, looking at that chart at C, we've got 21,500 BTUs per panel per day for the AE32. So that's really all. Just stick with the C, and you're the D is, see how much lower that is, but that's not, in this case, sticking with the C is going to be where you want to be. So it's right in the middle, and you're right in the middle here. We live in a climate that we're right in the middle there, and we're right in the middle there. So about 21,000 BTUs per panel per day. So when you go, I pointed that, when you go through that paper calculation, this basically explains how to do a water calculation if you want to get right into the individual use of water. I just said 40 for the house up there, but if you really want to study it, you can actually measure it. By the way, there's plenty of sites online that will tell you what the average family of 2 uses, 1 use, 4 use, so you can see how many gallons per day. But if you want to do it to your specific personal use, you can use this handout I gave you. Just follow through by actually using a container of a known gallonage and do your fill test and time it, and you can actually figure out how many gallons per water. Gallons of water you use, and then use this formula to work it out. Now this will give you, this establishes a number that you can actually go through and then use this list to follow through with it. But by following the handout I gave you there, I built in a factor here. It's just a 8.33 as a water density times the specific heat, which we don't have to worry about why that is. It's just, that's the factor. So we got 50 gallons. If you use 50 gallons of water times the degree of temperature rise. So if the water's coming in at 60 degrees and you want it to come out at, see, I said 80. If the temperature rise was 80 degrees, that would be 60. That'd be 40. That'd be 140 degree water coming out, which is sort of hot, but that's what some people use. Dishwashers, by the way, they have to use hot water for safety reasons, for cleanliness. So their water going in there might be, you might want it hot. So you multiply the 50 times 80 degree temperature rise times 8.33, and you've got how many BTUs you actually require for your use. So we know in this case, again, a little high. This does not reflect that house. This is just an example. In this case, 33,320 BTUs, but that panel's only give us about 21,000. So we're going to need 2 panels, or we're going to have to go find another panel, 2 smaller panels, or 1 bigger panel that's going to meet our 33,000. So that's all we need. That's the only part of this sheet we need to know, and we can go directly to that and figure it out.
What if we're building the panel ourselves?
It's going to be hard for you to know that. It's going to be very difficult for you to actually test. You might be able to take a pump that's going to replicate the pump that you're going to use in the real system, and pour in and set the panel up and have a container so it doesn't empty, and you know it's a 50, say it's a 55-gallon drum, you have 55 gallons of water at 60 degrees, and then measure the temperature of the water coming out over the entire 50 gallons, because you don't know, it may change. It's going to change immediately right away, but it may change going through. It's going to change because.
Hook the panel into a barrel right there. Run the pump that you're going to be using, and start playing with the temperature
right.
to see if you're where you need to be.
It goes.
That's a great idea.
Yeah, you're going in at 60, and then what does it come out as? And you know, oh, this one's only raising it up to 90 degrees. Well, I don't like that. Let's put 2 of them, or let's redesign the homemade one. Right. So that's about the only way to do it, easily.
Sure.
Yeah.
So these calculations are using a certain pump also, a certain flow?
No, they just well, they're using a known, a standardized flow. Yeah, they have all that figured out. That's because they all test the same way. So they typically pick something that the mean is going to use, and most, the majority of the people are going to be using, I'm not even going to explain the rest of this because that's, that basically has to do with the SRCC rating. We don't need that. It's already done for us. So trying to save some time on that. So let me see what else I didn't talk about that I need to cover.
The parts that we can do DIY,
yeah,
essentially,
that's out there.
Design,
yeah. Mm-hmm.
the panel.
Well, you can make the panel, yeah. Uh-huh.
I mean, design as to the flow.
The whole system design. Yeah, system design you can do yourself.
Panel.
Uh-huh.
Anything else?
You can scrounge around, and if you're really trying to save money, you can look for pumps on eBay, or you need a certain pump flow and head. How high does it have to pump? If you have 14 feet from you've designed your system. You've got your storage tank here. Say 12 feet above, you've got the collector, so you need a pump that has to pump at least, say, 15 feet to give it a little leeway. And how much flow, and then you can go look for a used pump that way, or a cheap pump. Let me see what else you can do. You can turn instead of using the purchased drain back little tank, you can buy another kind of a small water heater or a beer keg or something and do that yourself. You can do the mounting yourself. You can do the mount kits instead of buying that, you can use the mount kit. You can build a mount kit for your panels. You can do let's see what else. Well, you can actually turn a hot water heater into a solar storage tank by adding more insulation, really. I mean, there's no, the only thing you can't do easily is put a heat exchanger in it. They do sell external heat exchangers, and you can make one of those too. Instead of having the heat exchanger in the tank, they pump the water that's in the tank through a heat exchanger that's built right onto the side. They usually look like, and then there's still 2 loops, but the heat exchanger's outside. Normally, the way to do that is take a tube and another tube, and they're usually pretty big. So the inside tube is one loop, and the outside tube is the other loop, and they flow counter current. So one water goes this way, and the other one, the water goes that way. You can also build the way they do it in the beer industry and in the solar industries. They have what they call a flat. They have stacked plate. They have stainless steel plates, and then they stack them, many plates out. One hollow, and they space them apart by that much, very little bit, just like that. And then one crack is one type of water, and the next crack is the other type of water. One loop, the other loop, the same loop, and so every other loop is one supply, and the other, and what's left over is the other one, and that's very, very efficient. It's hard to make, but you can do it.
Are those commercial externals as efficient as an in-tank?
More efficient. They're more efficient. Yeah, they are. They're used very commonly in the glycol systems and in the higher end systems because they are very efficient. They're expensive too. They use them in the beer industry, like homebrew people use them, but they're little ones, so they can do their cooling, make a very efficient transfer of cooling. So their mash gets real hot, and you have to cool that down quickly. So you use that little plate heat exchanger to do that. But
how big of a tank would you have to have for that? For the coil to go around, like would it have to be an 80-gallon tank, or could it be small?
Oh, it could be smaller. Yeah, you could do that. You could also if you can weld, you can cut the top off of a tank and put the coils in there and then weld it back up again. You just fit the tubes out, and put the lid back on and weld it. That'll work. you know.
I thought about on a on an old gas water heater, you know, they have the empty, you can pull the coils
Yeah.
out.
Mhm.
And I wondered if you could do anything in the middle there.
Yeah, the middle, like I said, the middle is too small to. You have to have a certain amount of surface area to make it transfer. And the little, it's a 3 inch, it's a 3 or 4 inch, because it's a flue. I mean, it's a yeah. So it's not very big. Yeah. But I mean, when I worked for Mother Earth News, we built tons of hot water heaters out. I mean, solar tanks out of hot water heaters. In those days, the hot water heaters were a lot thicker, so they would last longer. You know, so you knew you wouldn't put all the effort into it, and next month it's going to, split. You know, so and these newer ones just aren't made that thick, but you can still find tanks. I mean, there's plenty of tanks available, and stainless is. Because of the beer industry and the liquor and stuff, that sort of the craft brewing, those things are a lot more available, and I'm not saying they're cheap, but they're a lot more available these days.
But it needs to be insulated, right?
Yeah, well, you can do that from the outside. Okay. Yeah, you can do that. Polyisocyanurate, or even better, spray-on, 2-part spray-on poly foam is the way to go with that.
Build it up.
Yeah, build it up. Just keep on layering up. Yeah.
Going back to the actual collector and do-it-yourself
Uh-huh.
mode, what do you recommend for materials? I mean,
I'm going to do that right now. We're just going to do that now because I'm looking at the clock and I'm trying to keep. So let's do that. Okay. We'll probably spend 20 minutes or so out here, and I'm just trying to keep my eye on the time so we have time to go back up. So the point here is to replicate as closely as possible the real one. The biggest drawback of this is the weight, but it's even worse than that. It's because it's wood. Wood isn't really the best choice of materials, but it's what's available, and it actually makes it really easy. The reason it's not is because they do get hot, and if in a drain back system especially, if it drains back for whatever reason and the sun comes back up, or let me see, I'm thinking of a situation where it's drained. If it got overheated and the sun drained back and the pump stopped and drained back, this thing would be exposed. This thing would be exposed to the sun, and this box can get hot, and they can actually smolder. So I want to make sure you know that, because I wouldn't want anybody building, say, 4 of these things full size and then figure out they don't catch on fire, but they'll. They can outgas, and that's not going to hurt you either because they're out in the open. But
would there be any issue with using a composite in lieu of lumber?
No, what I would do. In fact, we're going to do it. I just haven't started on it. What I would do is and I used to make them out of aluminum gutter. That's just not heavy enough. But stuff like this. See this door stuff? There is aluminum material out there. It's just the trouble is that as a retail buyer, they don't. And you can do it, but if you wanted to buy 4 10-feet lengths, it'd be incredibly expensive, and they just gouge you because they don't want to deal with individuals.
How about if you use metal tube optics?
You could do that, except they'd be galvanized, and it might not be as it might not be, because when you weld on that with a wire welder, it rusts after time. You know how.
You bolted it together.
Well, you could do that. I mean, yeah.
That's what they do in a commercial.
Right.
They just screw them together.
Yeah, sure, in a metal stud.
Yeah.
Yeah, that would work.
Metal duct tape or foil duct tape.
Yeah, foil tape. Yeah, that would be fine. I mean, galvanized. I guess I'm ahead in aluminum because that's the way that's a more weatherproof thing. But the galvanized is going to last quite a while. So yeah,
they're pretty cheap.
And they're cheap. That's right. Absolutely. Yeah, that would work. I mean, it has to be about 4 inches, 3.5 to 4 inches deep. This way, and it has to be strong enough. And you have to have a way to connect it, angle we're talking about there, angle iron, sheet metal screws maybe. If you can weld, you can use a cheap wire welder and do it. But that's the parameters, and being metal, of course, it's going to be weatherproof. And I mean, if it's galvanized, if it's aluminum, it's definitely weatherproof. It's strong. So that's the one thing. Sort of a disclaimer I have to throw out there. The wood is not really the best way to go, but it's what we got, and that's what I just want to show you this. So basically, what we've done here is I have not completed this because I wanted to show you, sort of what was in there. It's sort of a model. It's going to be finished, and we'll use it here at some point. But so what we've got is all the elements of a regular collector. We've got the frame, and we have a backboard that is plywood in this case is this, I know you can't see it very well, but it's underneath underneath the metal plates here. It's actually a black painted plywood panel, 1/2-inch plywood. Now I painted everything because this is going to be outside, it's going to be exposed. Most of the wood in here is treated lumber, but not all of it, so the plywood is and the frame parts are, but these other things I didn't cut out of treated, but I'm going to paint all that and really cover it so it'll be fine.
Is this plywood right behind?
Right, this is, yeah, this is plywood under here.
Okay, gotcha.
In fact,
There's no insulation, there's no rigid insulation under it?
yeah, I'm going to tip it. I'm going to kick it over here. And I only did this halfway so you can see. This is a polyisocyanurate insulation. So you want 1 inch insulation in here.
So you got 2 layers.
So I could only buy 1/2 inch. They make 1/2, 3/4, 1 full inch, 1.5 inches, but I couldn't find a local source for inch, so I just bought 2 1/2 inch. $19 a sheet.
Foil back is better.
Foil, the polyiso only comes in foil back. It's a special. Do not use extruded polystyrene, even if it's foam, even if it's foil faced. They make a blue board that's foil faced. Don't use that because that's not the same stuff. This is polyisocyanurate. The other stuff is extruded polystyrene. They're both poly, totally different chemical structure. It's just a poly based.
Because of insulation value or because of...
Oh, they're much better. It's not. It's because of the thermal qualities. The blue board will deteriorate in the kind of heat that we're going to see up on the roof like that. The other thing is this polyiso has a higher insulation value per inch than other stuff.
And the thermal faces the plywood. Is that correct?
The what now?
The
Foil face?
Foil faces plywood.
Yeah, right. Because you want the reflective value to be out, you know. So basically what I've done here is just make this box, external frame, and then laid a 1x1 strip, which I cut on the table saw, on the inside as a ledger as a base for the plywood. So you cut the, yeah, you can see it here. Cut the strips for the ledger, which is the base part, screw them in, and then cut the plywood to shape and size and put that in. And then I didn't put the insulation. I didn't even glue it in yet because I knew I was going to take it out again. But that goes in last. The insulation gets glued in there last. And to glue it, we use this stuff. Everybody's seen that at Lowe's or Home Depot. It's also an adhesive. It's an insulation, but it's also an adhesive too. I mean, it'll work as an adhesive, and it doesn't deteriorate the insulation. Some of these products can actually eat away at the insulation. You don't really want that, so this is a good choice. Oh, great stuff, yeah. You know, I noticed you're taking copious notes, which is great. I was a journalist for years, but this is all going to be on video, so you can review all this again on the page, on the website, so you know that. Okay. Let me see. So then we're trying to replicate that. So the only way we can do that is to get copper tubing and some kind of metal, flat metal. So our copper tubing, I chose 1/2 inch mainly because it's cheaper. This, when you go up to 3/4 inch, which is that much thicker, it doesn't just go up, you know, in a level curve. It starts going up. The thicker it is, the much more expensive it gets. So to build something in this thing, it's probably be $80 worth of copper alone just to do it that thick. The only benefit of this is it drains better. A 1/2 inch, you know, you have to make sure all your drain lines are as straight as possible, and not do too many horizontals, you know. So that's why we went with that size. So all I did was buy. They come in 10-foot lengths. These coppers, they come in 10s and 20s. The professionals use the longer lengths. They have the trucks to carry that, so they sell it in 10-foot lengths. I just cut. We know the boxes, and this whole thing was designed on the size of the materials you can get. Copper's available in 10 feet. This is an 8-foot piece. 2x4s come in 8 foot. Plywood comes in 4x8, so it's, you know, makes sense. I bought, you know, 1, 2, 3, 4. Let's say 1, 2, 3, 4, and like 5 pieces of 1/2 inch copper, 10-foot lengths. I bought 1, 2, 3, 8 T's. The T is, you know, the 2 side and 1 out here. And then that's essentially it. That's called a header. because it supplies everything equally. There's another header up here, which is black, so you can't see because I painted it black already, but it's up there. And then these long pipes just connect between the two things. So if I feed water down here, okay, well, this is another thing I want to tell you. I made them come out the sides because that's the way most collectors are built. But you could just as easily buy some more right turn 90-degree angles and have it come out the bottom, and then you wouldn't have these pokey things out the side. The reason I put 4 outlets on here was because that's the way the panels are built. If you want to be joining 2 or 3, you're going to need to have something sticking out. So if we're just going to have this one panel, we'd supply it from this side. Well, either side. Let's just say we'll supply it from this side, and then we'd outlet it from that side, and then we'd put a cap on that one and that one. If for whatever reason you wanted to feed it from this side, you'd feed it from here, put a cap on here, drain it from here, and put a cap on there. So that's it. It has to be opposite. If you're supplying the inlet water over there, you have to have the outlet water on the opposite side, because that allows it to fill the whole system and go out. If you did it on this side, it would want to only come up 1 or maybe 2 of these and do it that way. But this way, it forces it to come through the whole thing. So so that's that.
Does it indeed do that? Because all the pipes are uniform size, you're saying it actually will use all 4 of those pipes to go pretty well evenly.
It's the laws of flow in the water system. When you now there is a drop, there is a flow and rate drop, but it's only marginal. The further ones are going to be a little less. But when you do a system for, I work with the AET people on engineering design training and stuff. When you do, and a lot of the stuff they were talking about was industrial stuff, and of course I paid attention, but I'll never do it. But when you have like 12, 15 panels in a row, you have to feed them. You can't just feed at one end and let it, and then at the 15th one drain it there. You've got to actually have multiple feeds every 3rd panel, 1, 2, 3, and then feed another 1, 2, 3. So it does even out the flow. So it does affect it, but especially on something small like this is only 4 tubes. Normally this panel would be out here. Like I said, I didn't want to have to pick up that huge weight, so I just made a half of a one. So by the time you get out here, it will drop down. So but in this case, it's not going to be much of anything. So we have to figure a way now to get these plates attached to that and do it in an efficient way. As I said, these are high frequency alternating current welds. Very, very effective, very strong, and completely joining. So there's no place on here where it doesn't actually, where this tube doesn't actually touch that metal. We can't be that lucky. So what we're going to do is bend. Hang on a second. Let me get I have to get my metal in there. You can stay where you are. Yeah. I have to get my sheet metal. Oh, there. Where did I put that?
What do you need?
My roll of.
Here?
Oh, that's it. I thought it was a pot.
There's a funny kind of pot.
Yeah. Now this is. Now, another clarification here. It doesn't. You can use roof flashing if you want. It's very thin. It's commonly available. It's cheap. It's aluminum. That'll be fine. I really want something thicker because I wanted to have as much absorptive thermal storage, even in a little thing like this. We were talking about thermal storage before. A concrete floor will hold heat. Well, the same thing goes for here. You don't want it too thin because it's not gonna be able to really hold the heat. However, you don't want to spend, like $5 a square foot on the perfect material. So this is about as light and as cheap as you want to go if you're going to put the effort into building this. What I did was I found a source. I just mail ordered. You can drive up to the supply house in Asheville, one of those, the Best, or one of those places, more of a commercial supply, and you can get a thicker piece. But I ordered 7-inch wide pieces of heavier gauge aluminum. It's like a 18 or 19 gauge aluminum, so it's about twice as thick as that, if not 2.5 times as thick. And they come in sheets of, well, they come in different lengths, but I bought 4 4-foot lengths. So it's 7 inches wide, 4 foot long, I cut everything into 2-foot lengths. You don't want anything longer than 2 feet a section, because the thermal heating of it's going to buckle that. This way it's like a shingles. You've got it's not going to move that much. So these staples will be a little give to it. So basically, we got to turn a piece of that into a piece of that, because what we're doing is we're bending the plate to fit around the tube. And the way to do that is this. Basically, this is a sturdy, a fairly dense-grained species of pine or southern yellow pine. It's a little older. You could still get this. I mean, this just happens to be a little denser than normal. But I normally would use a piece of oak. I mean, you can get a piece of oak or maple would be even better. But basically, put this. I needed to find something else in here. Let me see if I can locate it. Oh, there it is. What you're going to do is go out and buy an $18 router bit. It's a 1/4 inch radius, and it's just almost perfect to make. You need a tool too. I didn't bring the router with me because it's sort of heavy, but you need to make a slot in a nice round shape in this piece of wood. So this is the template that gets hammered over that plate and makes that round shape. That's $18. The router I probably should have brought it with me. I found it at a yard sale for $30, and the price was right on it. So it's a good model. I've got a bigger one too, but the little one is what I used on this. And you just set the depth. The router allows you to set how deep this is going to chew. It just spins really fast and chews out the shape of this notch with a round bottom because it's made round. And you can set the depth, and you want it so that the fold occurs, so it wraps around most of the pipe and then goes flat. So I'm a little shallow, but that's just what I did. Then I routed that thing out there, and then in the part of the wood that was not part of the channel, I just put in 3 screws because you're going to be pounding on this, and you wanted to make sure it doesn't split. So I just put a long screw, drill a hole first and put a long screw, and then from the other side one other screw. They're 2.5 inch screws. So that's that, and then you just take your hammer and your.
Does it matter how much of the pipe is touching the fin?
Yeah, the more the better. In fact, that's what. I probably should talk about that before I cut that piece of metal. You want to get as close to what the factory did as possible. Now, to do that right, the transfer, just touching it isn't good enough. Silicone, you'd think that silicone isn't a. You'd think it'd be an insulator, but it's not. It's actually 5 times more effective to use this silicone as a thermal transfer paste between the copper pipe and the plate than as if we didn't use anything. It's not the gluing part that I'm looking for. It's the conductivity from the heat. So this stuff is definitely worth putting. It doesn't have to be GE. I mean, just any silicone. You just take the.
And that has a heat rating on it?
No, it doesn't. Oh yeah, it'll take the heat. Yeah. It wasn't designed for this purpose, but it does have a heat rating. Yeah. And you just ooze a strip in there, and by the time you staple it down, it just spreads it out and glues it, and also makes that thermal transfer. So that's one important thing that you don't really think about. The paint, while I'm holding products up, the paint is this is what I use. I've used this on my grill and stuff, and I've used it on my wood stoves. For the money, it's probably one of the better paints out there. I mean, it sticks good and it works well, and it it's fine. It's only $6, I think, for that. Sometimes Lowe's has them another third for the same price as value pack or something, and you can get extra. So that's the one I'd choose. Although any of them probably work.
Painting just the top.
All you're painting is the top of the plates. The copper you don't need to paint because it's going to be glued.
Paint the bottom, obviously.
No, it's just you could if you wanted to, but it would be actually you're going to be reflecting. It's going to be reflecting it back up again. So that's what you're really after.
So you're siliconing down the groove.
Just down the inside of the groove, because that groove, that's your tube. It's just going to go on there. We're going to lay it on the plywood. Start at the bottom, and then the next one goes over. So you have, because what's happens sometimes condensation forms. You want it to run off and go over the place, not find its way under. So so it's really just like laying shingles. You get this in here. If you could have a buddy help you or something, you could staple. You staple one course in close to here, and then you have somebody push from the other side. You can use vice grips or a piece of wood and some vice grips just to get it in there. People have made tools to actually clamp it out of wood again, like these screws that actually squeeze it and whatever. And I should say too, I just want to give the guy credit. I built many of these at Mother Earth and afterwards, very similar to this. This particular design, which is basically very similar to, there's a website called Build It Solar, and a fellow named, I should know his name. Chuck? No, not Chuck. Anyway, Build It Solar, and he does all these projects that have to do with solar energy. And this particular design is basically his design, but the elements are all stuff that we've all been using for years. He's really good at chronicling other people's stuff. Like he'll say, I built this and I put it online, and then Jeff so-and-so from Iowa did this little change, and Billy Smith built this tool to pinch these while you. So it's really a nice little sharing thing. It's called Build It Solar. It's really interesting. He's an unusual name though. Gary Reysa, that's his name. R-E-Y-S-E. So what we're doing is just stapling these. Make from the bottom all the way to the top till it's finished, and then in the stapling is how you're squishing that thing, and the silicone will dry after it's been stapled. And to do it the most easily, you take the plywood base out and do it without the frame. So you measure it out and make sure it's squared, and then you do it on the plywood base without, so the frame is not involved. Then you might ask, how do we get, you can't get it in. Then you take the side off the frame, just take the side off, and then slip the plywood in, then put the side back on. So that's how you get your tubes to stick out the holes, because you don't want to be able to. You can't really maneuver the grid in there with the sides on. Let me just see what I'm doing away at time here. So I'm not.
5:06.
Oh, okay, good, great. And then the glazing, and this stuff comes with. It's a polycarbonate sheet, $19 for this one sheet, and then they sell you these. These are made for like greenhouse roofing, for patios like this, all sorts of applications. So they have these things, these wiggle strips, that match the pattern of the bumps in this thing. So you can seal at the top. You just glue that to the there's a strip under here. Glue that to the strip, and then lay this glazing on top of that. And I've left this needs a lot more screws. I mean, I just did this so I could take it off. So up here you do that, and it's all sealed. And then down here you can do the same thing, and then maybe leave. You might want to leave a little notch, just to let condensation drain out, at the corners or something like that. So then once that's done, then you've got your glazing, and you just lay it on top of here and pre-drill holes with a good sharp drill, and just put these metal roof gasketed weatherproof. I think it's called WeatherTight. That's the name of the brand. And they have little rubber gaskets, so you don't want to crank them all the way down, but just compress the gasket a little bit. And I would put probably one every foot is probably what I'm going to do. And so, and that's really it. I mean, then, you know, you've got it. Make sure the, yeah.
Is there an optimum spacing where your pipes looks like you've got about 5
That's
inches there?
that's the thing I was just going to talk about. But before I get into that, I wanted to mention another thing. This is about the maximum width that you want to go before this stuff starts to sag, and it only comes in this width. It's a 26-inch width. So when you're going to build a panel this wide, if that's what you're going to do, like a full-size panel, you're going to have to, at this point, one's going to overlap, and then you're going to glue or silicone that, you know, the one covering to the next covering. And then you're also going to have to put some kind of a rod, and probably 2, steel rod or some kind of a rigid rod between, because we're talking about out here, you know, at least one in the middle and probably one here and one there, because that's what's going to, you don't want these, you don't want that glazing to touch the, you want some airspace between that. Because the energy has to come in, get in there, get trapped, and then bounce back into the black. So that's I'm just mentioning that because if you did go to build a full panel, you'd have that issue. Now that was a very good question. I want to be sure to cover that. How did I know whether it's 4, 6, or 8? What I did was I just extrapolated from an existing collector that I knew worked. I knew that a certain 4x8 panel that had a aluminum system that was really not a whole lot better than this one uses 7 up and down tubes at 1/2 inch, and it's a manufactured panel. So, and it works pretty good. So I figured I just divided 7 into 48, and I came up with 0.149 or whatever it was, and then I just extrapolated that, and dividing 4 into 24, it came out to 1.19. So I know I'm close. You know, if one was 15 and the other one was like 30, that would be way too many tubes. So I just tried to duplicate as many as close as I could to what I knew was a working system. You can calculate it out, but it takes time to figure out. What you don't want to do is, if you put too many tubes in here, it's not going to. You'll have to regulate the flow of the water through there, because the flow is going to affect how much hot water you get. If it's going to go slow, if it goes too fast, it's not going to collect the heat. If it goes too slow, it may not have enough. We don't know how much energy the copper can deliver to the water inside there. So, if you put too many tubes in there, you're really not going to have time with all that extra water flowing through there. The square footage of the panel is not going to be enough to feed all those tubes. You're not going to be using all the money you spent on those tubes to good use, because it's just not going to have enough time in the system to to supply the heat it needs. So this is about right for at this size.
Is the flow of water all coming up and then going out the top?
Yeah, that's the way they normally do it.
It's
Yeah.
not like
No, it doesn't do it that way. You can do it that way, but it won't drain. I kept it this way because this is typical for a drain back system. You can use this for a non-drain back system too, but a serpentine pattern, whether it's that way or that way, it's not going to drain because you're always going to have water at the bottom. So I didn't want to bring that into people's heads and have them think, because you might go home and build one and then it doesn't drain.
But it will all come up evenly. The air will go out as it's all
Yeah.
coming up.
Pat's coming in.
Can I make a dietary survey?
Yeah.
Do we have any vegans in our midst? You are or aren't a vegan? I'm vegan, but I won't be here. Aspiring vegan.
Easy.
Okay, so we will do a no bacon one then.
So don't worry about it.
No, it's fine. How about gluten? Any gluten people? No gluten allergies? Cool, that makes it easier. Okay, we'll just leave the bacon out of one of them. And the egg. Yeah. All right, good. Okay.
The question was whether the flow was even. Was that what you're saying?
Well, I didn't know which way the flow went, but
Yeah.
I guess as all the flow comes up,
Mhm.
it pushes the air out, so there's no airlocks or anything.
Yeah. Oh yeah. All the air gets shoved out. Yeah. Not that it can't airlock. I mean that does happen, but it's not. It's pretty rare. And before I forget it, the staples are stainless steel. Anything in here any nails or anything in here is either copper or stainless. I wouldn't, or weather tight type screws, you know, the really good weather decking screws or something. You don't want galvanized. You don't want stuff that's going to rust. And the other thing is that the aluminum and the steel together often cause it. We're using stainless, which is going to be less of a problem, but sometimes there's galvanic action between two dissimilar metals, so we don't want that either. Let's, before we go up to the house, which we're going to do, I'm just going to show you how I do this.
Now, is that similar to flashing?
It is flashing.
Oh, it is flashing.
This is flashing. That's what I say. It's cheap and available.
What's the upper limit on the temperature on the polycarbonate?
I'm not sure. It's pretty high though.
Yeah.
320 maybe or something like that. No, maybe not that high, but it's pretty high. It's enough that we're not gonna worry about it. Yeah. No, 320 sounds ridiculous. That's some kind of piping that I was thinking of. Wow.
That box could easily get over 200 degrees.
You can boil water in this one. Any of the systems can boil water easily. That's why they have steam pressure release valves. I'm just going to cut a rough thing so you can get an idea. Okay, let's go over to the table here, and I'll show you how it's done. You get one we don't care about. Let me see. How about over here?
I'm going your existing house.
Yeah.
Oh, I need a. No, I'll get the copy. Excuse me.
Yep.
Let me get that. Let me grab that piece of pipe. I have to do that for the hammering. You already?
No,
that's the most important thing.
So basically, what I did, and this is thinner, so it's going to be a lot easier. But basically, you clamp the pipe. I don't have the clamp, but you clamp the pipe if you can, but even just a simple clamp, so it doesn't. You don't want it to go this way or that way. If you have the ability, you can clamp it at both ends. Not so tight that it distorts it, but just because you're going to have to solder on there. But really, what you do is this is more or less just the model. You don't need to form them on the same pipe you're using, but you just cut a piece of pipe. So you clamp the pipe down, lay the thing over it like that, and you would mark it. I would mark it, for the middle. So you know you're always on the middle. You'd measure that, of course. And then you would take the swage block and hold it evenly, and I've learned that, just one there, and don't try to work completely on that. Then a little, start that one, and then that one, and then you can hold that. And this table's not the best example, but
you do a longer piece of metal though too. That's just scrap.
It's only 2 feet. Yeah, this is a scrap piece. It's only 2 feet. The maximum length of this metal is going to be 2 feet. So you don't want any more than that, because it's not only is it hard to do this, but it's also it'll buckle in the heat.
Yep.
So that's what I'm saying. You do this and you move it up, and you move it up, so you get your 2 feet. But this is I'm going to pick. That's where the strength is under there. So you can basically. I could work at it and make it'll be better, but that's really not bad. You get a good shape out of it.
The radiant floor places actually sell
Yeah,
metal like
right.
It's probably more expensive, I'm sure. But,
yeah. I mean, you could do it wherever you can source it. That's you ideally want a little thicker plate than this, because it'll absorb more energy. That's that's it basically. It's a matter of just dedicating an afternoon to making 36 of these or whatever it takes to, it's going to be what, 7, 4, how did I do it? 2, 4, 2, 4, 6, 8, 8 times, whatever, 4, it's 32 of them. Okay, so let's go up to the house and look at the system.
I have a question.
Yeah.
That I keep spotting.
When it's cold, 10 degrees outside, what do you do?
The water's always moving,
The
so
water's
it's not going to
always
freeze.
moving.
It's
Okay.
always on. The
So-
pump's
so
always on.
Even when it comes the first thing in the morning, it clicks on.
It's warm because it's in the storage tank. It's going to stay warm.
Okay.
It's
So
still
you're
it's
sitting-
warm when it comes up. Yeah.
Okay.
There's no water. There's no ice dams. There's no crystals in there really because it's all gone from the
So
collector.
even during an Arctic blast, you never just shut her down, just to wait it
No.
out, or
If that room that you had your storage tank in happened to be vulnerable to, if it wasn't a heated room and it really got cold and you thought, that way you might have to. I mean, that's just poor.
You can put a switch on and just turn it off.
Yeah, right.
And
right.
you wouldn't be hurting.
Yeah, that wouldn't matter.
Panels are snowed over. Could you just turn it on to get heat up there to melt them off?
Yeah.
Good question.
But the thing is that if the panels were, in that case, the temperature thermistor would have to say it was hot enough for that pump to come on. It's not going to automatically go. If that little sensor up there said it was still too cold, it's not going to turn the pump on.
Oh, it's not going to come on
Yeah.
if it's cold.
Right. Exactly.
So,
yeah.
okay.
You gotta have enough heat.
You got to have enough
So if
heat.
it's snowed
Wait till
over
it gets
for
the
3
sun
days,
comes.
you
Yeah.
don't know
Well, you have the backup element. That's the whole thing. That's there's always that element to back.
Except for those guys who are on 24 volt.
Yeah.
voltage.
Well, that's true. Yeah. Yeah.
Is there any problem with this being like a thermal mass on your roof, like making your shingles buckle or anything like that? If you
No, because they're up on stands. We'll see how that.
Oh, okay.
I'll show you how that works.
Why do you have it come out both ends when you only need one on one and one on the other?
Because I'm going to put another one next to this, pair them. A mate to this is going to go up. If I wanted to make a bigger
I see.
system,
So
then I have
if it's by
couplings.
itself, you'd only need.
Yeah, if you just have, if this is all you're going to do, I wouldn't even bother with. I would just put a elbow at that point.
Okay. Okay.
Let's walk up to the house. So that's basically your two panels. The water feed is coming up from the lower corner here. The pump is in, and I'll show you in there. And then the water's going up into the first and second ones, flowing up through and then coming out the very top, back down, behind the panel, and then back out. So, and the
utility room's right underneath there.
what's utility room is right behind that gutter, on the other side of that wall. Let me see what else I can say about this. That particular mount is called a standard mount or a triangle mount. They often have another kind of a mount which is more of a rail system. It's like a solid rail that goes across, and there's these special clips that clip onto that, and you can adjust the panels really easily, right and left. And that helps when you're trying to mate them. You're trying to mate this union, see where they join? When you're trying to get everything lined up and get them together so they don't leak and all that.
And those are 1-inch connections on there.
All the collectors have 1-inch connectors, and then they reduce down to 3/4.
Okay. You can't reduce down any smaller. Than
No, 3/4 is the minimum. You can use 1-inch through, but when you start buying 1-inch pipe, it's
Copper,
expensive. Yeah. And as I said, the solar loop has to be copper. I mean, you really don't want to do, in your home built system, if you want to try to build it in PEX, that's fine. Oxygen barrier, hydronic heating PEX would be what I'd try, the 180 degree stuff, but you're going to get higher. You could very well get higher than 180.
Wow.
I'm not to say that you will, but you could.
At least the top coming off of it should be copper. If you just had a little money to spend.
Yeah. Yeah, I mean, I guess if you insisted on using PEX, you could make that happen once it got in the house.
Yep.
Yeah. But I don't know. We capped that corner, and then fed here and drained from there. At the very top, you see that wire? I still haven't wrapped it in. There's a sealant. There's a UV-proof tape sealer that goes around the insulation. But see that wire goes up to the very corner there. That's where the thermistor is for the outlet. That's where it's a little bulb about that long and about the size of a pencil. It gets clamped to the very top pipe, so it reads the temperature just as it comes out of the collector. So that's critical.
It doesn't actually go into the collector.
No, it doesn't. They do make they do make a fitting that has a threaded thing that you can actually screw one in, which is more positive. But this is just a clamped on, very simple.
Can you protect that in some way so that
Well, it
it
is.
doesn't get snow on it?
It's underneath the insulation.
So that's
Yeah.
what you normally would
Yeah,
do.
yeah, it's under the insulation, and then we're going to tape that insulation all around, fix all that up so it's UV proof. And those struts, they come in 5-foot lengths, and you cut them. That's the height. You cut them. If you want less, you can cut them. You can get 6-foot lengths, but again, the wind load you know, when you start getting a big sail like that on the roof, you start worrying about it's going to rip the rafters out at a 90-mile-an-hour wind, you know. And what I am going to do is go back. I didn't do it. And bridge instead of, right now, every mount is into one rafter, and what I'm going to do is bridge underneath, connect 3 rafters, span them. So if it has to pick the roof up, it's going to take the whole roof with it, you know. And you can see what I said about the skylight. There's your front skylight for the workroom, and the other one is actually hidden, but you still get light through it. It's a hallway in there. You can't see it. It's back in there.
Is that dumping extra water though, right at your skylight, where you might have problems, or not?
Well, we'll see. Yeah,
okay.
you are right. Yeah, yeah. I mean, that skylight has leaked.
Has leaked
before.
Yeah,
yeah. You solar, but you have to see. We could have put it up here, but then we would have hit into that that vent unless I came up really forward, and then I would have had to do the horizontal, more of a horizontal run to the only place I could put the tank, which was the garage is definitely unheated and definitely can get to freezing, whereas that little room doesn't.
Okay.
And if it got to 30 degrees, it's only going to be for, you know, 6 hours in a night, and the water is going to be plenty warm it's not going to freeze, you know. At least I hope.
And you insulate the pipe all the way down, like
all
on
the way,
other
yeah.
side.
And in the house and everything, yes, totally insulated. Everything has to be insulated. It's not just for the freeze protection, but it's also for the heat protection. You want to maintain as much heat as possible in that pipe on the supply side anyway, on the heat side, you know. And
what is this smaller copper tube?
Oh, that's the wire chase, the little hook.
Oh, okay.
That's where the wire goes.
Okay.
You can see it coming out of there.
How do you make your penetration through the roof with your plumbing? What kind of?
1 1/8-inch hole, and then there's a copper for the bases. For the actual supports, there's a galvanized plate which you mastic, and then there's a seal at the bottom of the underside too, where the bolt goes through, and then you mastic the bolt hole, and you know, it should work.
Do they make special plates?
Yeah, that's what those are. Those are little domed plates. They have a little relief.
Or where would you get that?
I bought those from AET, but I think you could probably Google a solar mounting flashing or something like that.
Those panels are glass. And this whole system came.
Wait a minute. Let me just answer his first.
It's a glass glazing or polycarbonate?
No, it's glass. This is all low iron glass. Yeah.
Oh, that whole system was bought together with the tank and everything?
Yeah, I just picked everything out and we just made a package out of it.
Yeah.
Yeah. Yeah. And I could do individual. I could have made it a AE40 to another kind of a tank. If I didn't want to buy the tank from them, I could have just say, don't sell me the tank. I'll get that someplace else. You know, you can do that too. Yeah. It just makes it easy, you know, as a package, because they know it pretty much makes it.
Things work together.
Yeah, yeah, and they always do that. But I did change. I changed the mountings, and I did something else. I changed a little bit, but that wasn't a big deal.
Tanks?
Yeah, we're going in. Yeah.
The mounting, because I have a panel very similar to that with nothing else.
Yeah.
No instructions. Can I get those mountings from AET?
Yeah. Mm-hmm.
Awesome.
Yeah, if they fit your panel. I mean, you know.
They look standard. It
Yeah.
looks just like that.
Yeah, they are pretty standard. You have to, if you tell them the panel you do have, then they can tell you if their stuff fits. You know, they don't sell retail. You have to find a dealer for. That's the trouble. I mean, the fellow in.
Maybe apply to be a dealer.
Yeah, well, yeah, the fellow in I think it's a Charlotte dealer.
Okay.
Yeah.
In these pre-made packages, do they have any kind of an alarm system if you had a water leak or?
No, I mean you could put one in there, but I've never seen. They might have an audible alarm on some of them. In some of the controllers, they actually have an audible alarm, but that's not so much for a leak, but it might be for the pump's not stopping and it's supposed to be, you know, something like that, you know. Okay, folks, let's see. Let's go in. We're going to go and make a left turn. Excuse me. Okay. So basically, oh, nobody's not here.
Right. Well, then I do have a fire pit. I can, you know, things have more time on my hands. And things get that bad.
It's just resting now because we've already achieved the differential. We haven't. We've already got to where it's made as much hot water as it can make, and not, we don't need any more out of it. So and the temperature of the sun, since it's clouded and late in the day, it's not. And remember, we have blocked after 3 o'clock. We've blocked most of the available sun, almost all of it. So, at this point, it's resting, so it's done what it has to do. But this is the pump. This is the storage tank. This is the little drain back tank. This is the sight glass, so you can see what's going on up there. This is the pump and the feed to the bottom corner of the collector, and then over here is the return from the top corner of the opposite collector into the drain back tank, and then it's drained, So let me see what else we have. So that's the loop. It just goes here, down to here, into the inlet for the heat exchanger, which is in the tank, and then the outlet for the heat exchanger. Let me see where is down here. So it's just going through, coil through bottom of the pump, up it goes, and back again.
And this is the lower thermistor here.
Yeah, that's reading the temperature, the tank temperature, and the upstairs one is collector one is the collector one.
How big is the coil that's in there?
They're, from what I saw in the factory, they're about that big, and they're about that tall. I don't know how many coils. It's probably at least 10.
Feet?
They told me, but I don't remember. You could probably get that information online. I know it'd be nice to know if you're making your own, but I would think it's probably going to be 60 feet.
And
something like
volume
that.
of that tank?
80 gallons.
That's all?
Yeah.
This is being used for domestic hot water.
That's all. Yeah.
And so that comes out.
Oh yeah, that's the other part of this. Now, I was thinking about something with you. Oh, the reason it looks big is because there's there's like that much insulation in it. So the tank is actually pretty skinny in there. So the circuit here this is the cold water line from the supply that normally would go to your regular hot water heater. So I cut that line and fed it over here. So this is your cold supply, like you'd feed your toilet or anything. And then you're going into the system here, and then that's not part of it. And then it's going into there. That's the feed for the tank. This part is the feed. That little branch is the feed to the water mixer, the mixing valve that I talked to you about. So if the water's too hot, the mixing valve's gonna need some cold water to temper it. So that's the supply for that. It comes out then. You really can't see it, but on the back side there's a fitting. Yeah, on the back side there's a fitting, and this pipe comes out of the tank and goes. Then this red hot pipe goes into the inlet of the existing water heater. So it's really acting as a preheater for the existing water heater. So.
But the hot's always at the top, right? The hot outlet.
Yeah, right.
And there's no need for a pressure tank because it actually interfere with how this works.
Right. Yeah. There's no pressure tank, and no, it's not a pressurized system.
So I'm sorry, is that the pump there?
Yeah, that's the pump right there. Yeah. Yeah. So and to feed and to start the system when it's empty, like when you first set it up, there's a boiler drain there that drains the system, and it also is the feed. So you put your garden hose in there and just feed the thing up.
Until your bubble is right up here?
Yeah,
until everything's done.
Until you're up to about.
Right.
Yeah, you're up to that point where when it's drained, when it's operating, the levels here, and when it's drained, it's higher.
Well, it's drained now, isn't it?
Yeah, it's drained now. Yeah.
And do you change that out once a year?
There's a rust inhibitor you can put in there. You don't really need to change it. Some people put distilled water in, but it can get expensive to buy the distilled water and do that. The other thing is it's a single wall heat exchanger. So the code doesn't always allow you to put a glycol mixture unless it's a non-toxic glycol mixture into the loop, because if the single wall heat exchanger there's only one wall, so if it failed, it would mix right with your hot water. You might get it in your mouth, in the sink or something. So you have to either use a non-toxic glycol mixture, which is available, or you can just use pure water, which is much better. Water has a much better thermal transfer value than glycol in water. Glycol in water, when you mix it, will reduce your thermal transfer by 30%.
Oh, really?
Yeah. Yeah. If you use it to the mixture that they recommend.
I thought maybe it'd be higher.
Me too.
Yeah, 30%. So.
Second grader question.
Yeah.
When you're filling the system, how does the, it goes up, it starts in here, like from the garden hose, goes up, fills everything, comes down into the drain bank.
Mm-hmm.
How does the drain bank know not to fill up? You know what I mean?
You fill the system.
Overfill, you mean? Or
Yeah, when they're filling it.
Well, when I fill it, I look at the sight glass, so you don't.
So,
you know.
okay, then the
I know I don't
drain-
want to go. I mean, I just
Right.
guessed I don't want to go any
Yeah,
higher
no.
than say 3/4.
Right, but why doesn't it fill up and then, you know what I'm saying? How does
Fill
it just
up.
fill
Let me
up
see.
that way?
I'm pumped. It'll choose as you.
Because
Yeah.
it drains down low. I
Yeah.
guess,
It'll when you first fill it up, it'll choose. Some of the water is going to go up to the collector, and some of it's going to go. It's just going to go through this way. It's going to go the other way, and it's just going to fill it from both sides.
Oh, okay.
Yeah.
Okay, gotcha.
Yeah, because it knows there's two openings. It's going to pick whatever choice is of least resistance, and that may be a little different between the two pipes because there's a pump involved here, and the other one doesn't have a.
But it's a closed system, so
Yeah.
you're not thinking that it's going to go into the tank, though. Is that what you were thinking?
No, I'm just thinking, to me, my crazy logic is that you'd have to fill that thing up if it was a one-way system.
Yeah.
With water, you'd have to fill that up.
No, it fills from both sides. That's basically it. It comes up to that point, and then you can get an airlock. I mean, and we're still fooling with this. I'm going to do some adjustments on the limits and just see what's going on because we have this unusual situation. Normally, the only thing unusual is that I'm tying it into the existing tank, which people do that, but that's not as normal as just using this as your water tank. This is your electrical element at this point. There's only one of them. I didn't even hook it up. The outlet is right here, and I'm not even going to hook it up. I don't think I'm going to need it because the water tank in there has one.
So what if, without your labor, what's the cost retail of this whole thing we're looking at?
Let me see. It's.
Just a ballpark.
No. I'm trying to think of this. This system is to qualify. This is a stainless steel tank. It's the Cadillac of tanks. So it's not just your regular tank. So that adds a lot. And then the panels are both AET panels are not cheap. They're high-end panels. So the whole system is probably you're looking at about probably a little over $5,000, something like that. With all the pumps, the tanks, the two tanks, both collectors, the mounting kits, something like that.
What about just the two tanks?
I don't know the prices on all the tanks because they wouldn't tell me the price on the tank because she had a good reason. It was a proprietary thing, but I don't know. I guess you could look at them around $800 for a standard tank. These are
Maybe $1,500 those two tanks.
Yeah, probably. Yeah, I would say that could be. Yeah, that's right.
If you were going to hook up a Rinnai as an alternate
Mhm.
energy.
You mean a backup?
Yes.
Yeah.
Where would you put that in here?
In the system?
Would it matter how close it was to?
Well, you first think about siting it where you can exhaust it, the direct vent. That's one thing. And then the other thing is you could do it to preheat the cold water going into the system, or you could do it to preheat the cold water going into the other one.
Do you want to
Yeah.
save propane or do you want to save
Yeah.
hot water?
Well, I wasn't really thinking that you would use another tank.
Yeah.
So,
Okay. Yeah.
Just Rinnai and this.
Yeah. In that case, they'd probably put it after the tank and just boost it before it got into your system. Into your faucet. Yeah. So, I don't know if anybody wants to. They really. Yeah. I know you're not going to crawl under there, but it's probably not that important. But the way I plumbed it, I just cut under there. There's a valve. I routed it. I isolated this whole solar part so that if we had to work on the system, we just turn one valve off and two valves off and one valve on, and that isolates this whole system so he can use his existing hot water tank, take showers and water and all that. Yeah. And the way to do that is to just have a cross with the valve in it, and then each of these lines has a valve in it. So you can either You can either open the cross and let it just and then close the other one so it completely cuts this off, or you can open these and close the cross so it has to go through this and back.
So you could use either the solar or you could use the
Right,
electric.
right, and mainly not so much for the choice, but mainly for working on this. If I, so he can still have hot water, and water while I'm working on it. Because what if I had to order a tank and it took 4 days? That kind of thing. That's all.
A bullet hole, something like that.
Yeah. We can go upstairs if you want to, but it's the steps are narrow. No, I'm not saying we can't, but you can almost see it from. In fact, you can see it from here. So there's no real point in going upstairs. If you want, there's the downcomers from the. I can stand out here and still talk. The downcomers from the solar collector are right in the corner. The straight ones coming down, and then these are the connections between the tanks.
Okay.
All that happens behind that wall.
So this is the power cord and this is the sensor?
These are the sensor cords. That's the one from the collector. That's the one from the tank.
So
this is the power cord, and this is the, once it goes through the controller, this is the pump power cord.
Oh, okay, cool. Wow.
Yeah, right.
So that's like
Load.
brainless electricity.
Wow. Electrical knowledge, yeah.
And there's no real maintenance to this one.
No, I mean, I wish they would have supplied us with a bronze pump. It's a cast iron pump, and cast iron pumps are normally used in completely pressurized closed systems where there's no oxygen because iron rusts. So in the cases where there is oxygen, they're supposed to give you a bronze pump, which is more expensive. They didn't do it wrong. It just wasn't what came. So what they did, we have an inhibitor. We have a rust inhibitor that we can put in the system to help that. But the maintenance would be the pump could it could break. There's really nothing you can adjust. I mean, it just doesn't. It's on, just on. And if something breaks, then you just have to replace it. And that's almost always going to be the pump. And the only other thing it might break is that might get, if lightning might hit nearby or something, it could be sensitive to electronic impacts. And in the back here, there's a mixing valve, which is adjustable. You can't really see it, but it's back in there with a big red knob on it, and you can turn that to make it adjust the flow of temperature of hot water into the tank.
Tee off your cold water to supply that? You're just coming off your cold water supply?
Yeah, it tees right down here. Yeah. It's the cold water supply, but you pull off of it to feed the mixing valve. It's right here on the side. And everything's copper except for once we get to the outlet, then we went to PEX because it's so easy to work with. Let me see.
They're losing a lot of heat through there, aren't they? Wouldn't you put like plastic up for the sunlight? Or
you mean in this room?
Yeah.
Oh yeah, we could do that. I put plexiglass in the other skylight for him.
Yeah, I was just curious.
Yeah. Yeah, you're right. Absolutely. This house, actually, I didn't mention it. This house is sort of a research model. I've been doing energy efficiency improvements. We did a control, and we knew how much energy you used beforehand. Then step by step, I've been doing little things, and we're working our way towards and recording everything, working our way towards how much improvement we can make with each step.
You don't want to do it all at once.
No, you don't. You know, expense-wise, and just you wouldn't know what's going on.
You'll also insulate all of
Yeah, oh yeah, we just didn't do that. All this has to be insulated in that thick foam that we saw outside. It's a Armorlite. I forget the name of the. It's a closed cell, high density, 300 degree. Yeah, that's what it is. 300 degree.
Boiler.
Yeah, boiler stuff. Yeah, so it takes very hot water.
You'd get that at a water.
You can get that at any plumbing supply, or you can get it. You can order. We order it from a company called Zoro, Z-O-R-O, or boilers, or heating supply company.
Okay. And shark bites are fine to use.
Yeah, I don't really like them, but they didn't seem to leak. So
okay.
Yeah, they're available.
I wondered about the high heat.
Oh, they're fine. Yeah, they're fine for that. Yeah, I'm just the sweating. I'm just used to sweating and the fittings, and I think it's just old school, but it works. It's a lot more time, But we're going to be running a. I'll announce it when everybody's here too. But we're going to be running a little mini skills course on just plumbing how to, sweating pipe, what kind of pipes to use, what's the difference between PEX, CPVC, PVC, polybutylene, copper, iron. bending the copper, which we did over our knees, but there is a tool to do it.
And there's a flexible copper.
Well, that's this.
Oh,
This is.
I was taught to do it with heat.
Well, yeah, you can do that. Yeah, you can do that, or you can just put it in the bender, and you know.
Or ice. I've heard of ice.
Yeah.
Ice.
Yeah.
Ice.
Well, any other questions about this? We can walk our way down, and we can eat, and we can answer. We can have sort of a question and answer time.
One of those big panels, and they had a little tabletop.
Oh
Those
yeah,
are
the
like-
demo. Yeah, yeah.
Yeah, and it's got a little gallon per minute and a little pump and
Yeah,
a valve.
right,
I took
right,
the tank off, and I salvaged this electric water heater. That's
Yeah.
you know, and I was gonna run it up. It's concrete floor with drains. Going to be a greenhouse bathroom.
Yeah.
And was gonna run it up there, and I have a big panel too.
Uh-huh.
So I have this little system, and then I have a bigger panel. And I didn't know how to make that work. Like you say, I still need electronics to turn it on. And
Yeah,
off.
yeah. You need some. I mean, you can do it. It can be done manually, but you're never going to remember every time to do that.
No.
Yeah.
But with the water, with the sun, it all depends on if the pump would have a
check valve. Well,
check valve.
Yeah,
Yes.
yeah. It has to be free.
And it's unlikely it would. Or.
Most of the time they have check valves in them, but they also can be removed. They're made to be removable.
Oh, okay.
So you might check that out. They usually say turn the pliers in there and turn it half a turn or quarter turn clockwise and counterclockwise, and it comes out.
And to do that, then the only thing I might be, if I could do that and it would come on during the. Do you see any problem with that? Where it come on, I would need a drain back tank.
Yeah.
It would come on during the day, pump.
And keep on pumping.
Pump.
Yeah.
The sun goes down, it drains back.
Yeah, right.
And what problem is that? Well, it's
Really not a problem, except that you have to have some mechanism to tell the pump to stop when, well, yeah, when the temperature reaches below a certain.
Could you just add extra emergency valve to blow hot water off if that was, also.
Yeah, you can do it with a valve. Yeah.
I was thinking about really. I'm on a south-facing ball, super sunny,
Yeah.
Tennessee,
Right.
hot.
Right.
I'm thinking put the thing up even more. Just for the winter and the summer. I mean, it's hot up there. I can imagine boil it almost just on a normal day.
You can buy a. In fact, they have them in each of those tanks has a not a pressure. Wait a minute now. There's TMP. There's one TMP temperature and pressure, and then there is a temperature relief valve on each of those tanks in addition.
Built on?
Yeah, built into the tanks. Yeah.
Oh, built into the tank.
And right on the side, they come up.
But if I didn't buy the tank, I was even thinking about.
No, they screw it. They screw it.
Like you used to have on a water heater.
Yeah, right, just like that, yeah.
But it's rated a little higher.
Yeah, right.
And could I screw that on the outside of that collector since I have 4 ports and I'm only using 2?
Yeah, no, because the sensor is like this rod that goes in, and I'm not really sure.
And it blows it out, but does it automatically reset when the temperature drops?
Yeah, they. Well, wait a minute now. They usually, if they really pop out, they stay out. That's the trouble.
Out.
Yeah.
Okay.
Yeah.
Okay.
And when they get old, once you, let's say,
yeah,
it's hard to seal once it's been used once. Because they're not meant to be used all the time. It's meant to be, it's emergency. Yeah.
2 or 3 times in its life, maybe.
Yeah. Right.
Okay, interesting. A lot of food for thought.
It's not that simple. I mean,
no.
That's why it's taken so many years to develop the systems and mature them.
Yeah.
Yeah.
Well, when I get a concrete floor and I ran.
So, question: are you done?
I'm done, except for the question and answer stuff.
Well, I
we're going
could
to eat.
go on for all night,
Yeah.
so-
Okay.
Yeah.
All right.
That's what we said we were going to do. Is after we eat, we'll have a little time for.
Okay. Because I plan usually on having the food at 6:30.
Oh, he said 6. Somebody said 6. Oh, I'm
Usually
sorry.
do 6:30.
Oh, okay. We can do the question and answer now then.
Yeah, do
Let's
question
that.
and answer, yeah.
Oh, shit, I'm sorry. I thought 6. That's what I was.
Yeah, usually because we end at 7. We do
Okay.
the last half hour.
Okay. Trying to think of anything we didn't talk about that I was supposed to talk about. And then, like solar pool heating. I mean, that's all sort of different technology. The collectors are different. They can use to heat a pool. You can use the regular flat plate box collectors like the house, but they're sort of expensive. What they normally do is have a rubber. It's a very tough rubber sheet with built-in channels in it, and then they lay them down, and they're a lot cheaper, and so you can put more of them, and they just pump water through and heat the pool. Use the pool water is the medium, so it works out.
That's pretty inexpensive and efficient. Yeah, they have those plastic things too, right? You can just roll that on the roof.
Yeah, yeah, they sell those on the internet. That works. This is sort of a sophisticated version of those, but they, they're not as efficient as a regular collector, but they're certainly cheap. And what we use them for, we salvage some. We use them for our growing beds. Underneath the growing bed in the spring when it's still cold, you just lay that down first and put the soil on top of that, and pass hot water through it. At our other facility in Grandview, down the road here, we have a biochar facility, so it makes a lot of hot water, and so we just divert some of that for our growing beds, and so we get.
Well, that was thermosiphon also, right?
Well, we pump it.
You pump it,
yeah, because they're too small to really thermosiphon.
Well, if you did that with solar, it would.
Well, when you get tubes, those are really little passages. When you get something that small, it doesn't thermosiphon very easily. And that's the other thing I really didn't talk about. I had pictures of other types of systems, but there are batch systems, and there are other types of systems that work like for various reasons.
Well, so like if you wanted to make something that was just to give the horse a bath.
Mm-hmm.
So it's only when it's kind of warm anyway, and so you could have a collector down low and a
tank on top.
Tank up high.
Yeah, that's a typical batch system.
It would just
yeah, that's exactly what they use in Bermuda and Haiti and places where they need hot water, but they don't have a lot of money. They take a collector very much like that, and put in usually bigger tubes, but they'll and it doesn't have to be copper. I mean, because they have so much intense sun down there, and then at the top of the collector they have a sideways tank, and it's just a loop. It comes in the bottom and goes out, and when you draw out hot water, just the cold water supply comes into that tank and gets mixed with what's already there, and it makes the only thing wrong with that is that it freezes, and in your horse situation you're going to drain that after the bath. Yeah, you're going to manually just open that valve and let it, or you're going to use it all up. You're not going to put any more back in once because the tank's high enough it'll gravity feed. So that's the way that would work.
Yeah.
And when you see the water heaters like above, I know that's an older type.
Yeah,
but just
that's the batch heater. That's the same as he's talking about.
Does it have to be on top of that loop?
Yeah, because that's how the siphon works. It has to be on top like that.
Okay. And the only thing, if you did something up for your house, though, the downfall, come your first frost date, you would want to empty it.
Yeah, you have to remember that. That's when they design these systems. They have to be fail safe and human proof, and humans have a tendency to forget stuff. Oh, yeah. So what happens is, because you've forgotten to drain the tank, they get a bad reputation for cracked tanks. Yeah. So they don't like to do things that way. They want a foolproof system. But as I said, many in climates where it doesn't freeze, those things are real common. The only other problem with those is that they're heavy because they got all that water, and so when you put it on a roof, you just chuck it up on any old roof. You have to either bolster the roof up or make sure that the roof you're putting it on is strong.
In the Middle East, they use concrete roofs.
Yeah,
so
right.
they don't really need to do anything.
Exactly.
They can put 3 and 4 tanks on top of it.
Right, yeah. And that's what I said in hotels I've seen in Cyprus and Israel and Jordan and a lot of places. They have those concrete structures, and all the roofs are filled with solar collectors. Yep.
So is there a formula to? I mentioned mass, thermal mass for tables for greenhouse. Is there a formula for how many gallons you can heat up to a certain degree with a unit like this?
Well, there is, but you have to know the density of the concrete. Concrete comes in various densities.
I'm not talking concrete. I'm talking about
just a table.
55 gallon.
Oh, the drums. Okay, that's right. Yeah. Well, yeah, because water. There's a temperature drop of. I don't have it in my head, but there's a temperature drop through steel, so many degrees per hour, and you have so many gallons. So then you can figure the loss per hour and how much you have to feed in BTUs. It's losing 10 degrees and 5,000 BTUs every hour. Mm-hmm. So then you have to have a collector to feed 5,000 degrees every hour back into it. Mm-hmm. So that's basically by reading that chart that it was on the SRCC thing, you can do it that way.
Yeah. It's just there's no usage of water. It's just being circulated.
Just be circulating, yeah. So it's but it still will use. I mean, it still will transpire the energy out through the, through the barrels. I mean, it's going to be going out because it has to heat the air.
Highly dependent on the temperature in the greenhouse.
It's the whole thing's based on differential temperature. What your water's coming in at and how much is oozing out into the air and how cold the air is. Yeah. And then of course that changes because the more warm air you feed into that greenhouse, the hotter it's going to get. But then you have to figure out the heat loss, and they do have figures for that. What the heat loss is in a greenhouse of double wall, like we have a double wall greenhouse with air in between. We know that of a size like that, it loses so many BTUs per hour. So we figure that in too.
Yeah, I went to a greenhouse. Like I said, I've been doing this research for probably about 5 weeks now, and I've went to several greenhouses. And there was one greenhouse where she doesn't. It was she used the plexiglass, plexi, something like that.
Yeah.
The one,
right.
Yeah, on one side, on the south side, and she used a 60-degree angle facing south, and it was very technical. She said she should have used 57, but she 7 degrees, but she never had to use any heating. She says the water temperature and the barrels, stays above that without any solar. And that's why I'm surprised why one of these or two of these will not, make it for something.
Yeah, make it work. Yeah, it just there's several different factors involved, and the building is very important. Like how much heat loss is going to leave the greenhouse. Yeah. That's obviously pretty important. Yeah.
I think she had like about 24.
What do you think about heating up barrels instead?
Well, that's what he's talking about.
And
yeah.
The green and the blue and the red.
The different colors?
Yeah.
Well, no, because remember that guy. I forget the name of the son.
Passive solar guy.
Yeah, passive solar guy. He talks at a lot of the events. He has a greenhouse company. He insists that the colors, he uses green and red barrels, but really, and he insists that they've tested it, but I haven't ever seen. The only thing that even comes close to flat black is a very, very dark green, very, very dark green, like a deep blackboard. The old blackboards are the really deep green. And they have had some success with that, but I don't see where red and that's good for filtering light colors for plant growing. That's different.
What's his name? The guy that
They do passive solar greenhouses.
Yeah, it's a passive solar greenhouse. I just don't remember the name. I don't remember. I'm sorry. I'm not that I'm.
It's not the permaculture guy in Colorado, is it?
No. This is a guy that lives in this particular guy. I'm thinking of lives.
In the CFSA area.
Yeah, he lives up in Madison County. I just don't remember his name. Yeah, that other guy is John Haidt. I think you're talking about in Colorado.
He runs the Colorado Rocky Mountain.
Oh, that guy.
I'm reading this book. He's doing these underground thermal batteries.
Yeah. Oh, yeah.
Blowing the air in and out.
Right. Yeah. Amory Lovins. That's who started that. He does all his energy analysis and feature. Talks about pretty interesting because he talks about like it'll take. What's the impact of eating beef? And then he says that to raise 1,000 head of beef cattle in a year, it consumes 947 football fields, 6 feet deep. So he gives you a good picture of how much you really, you're paying to eat that beef. But it's.
I had a question about. I asked you about using a system that you had described, that was pictured.
Yeah.
And having what I'm looking at is maybe one tank, not an extra storage tank, but I would like to heat, if possible, a small room to keep it kind of temperate.
Yeah, right.
And I'm talking like a 4x5 or a 5x5.
Oh, it's a very small room. Yeah.
Really,
Okay. Yeah.
Closet. And my question is, you said that could be done.
Yeah.
Where do you tap? You just use the exiting hot water that you would normally use?
I would pull off. Well, first of all, I just before. Really, it takes about 130-degree water to make an effect on the air because it has to go through a radiator of some type of a liquid to air heat exchanger. So, and when you blow, and to make that really work well, you usually put a fan behind it. Now, in a small room like that, it's not inconceivable. It's just the oozing of the heat off the fins. You're not going to need a fan. So so your temperature may not have to be that high.
Well, this gets down to.
Yeah.
I mean, it's like 3,800 feet.
Yeah.
It's about I've seen 0 and
yeah.
below.
Right. So. So I would pull. You can just pull off of a loop from that, from that exiting hot water.
Okay.
Yeah.
And then run that through PEG.
Yeah, right, PEGs. Yeah.
Okay.
Yeah. Do it that way. But.
But that's generally the idea with the space heating is you have the packs with the hot water and you got a fan over it.
Well, in radiant floor heating, that's how they do it. Oh, you mean
Like
with the
space
fan?
heating.
No. What they have there is a unit. I don't want to walk all the way down there, but you can see the box. Can you see that outline of a box in the back of that greenhouse is hanging from the ceiling? All it is a car radiator. I mean, it's not a car. It's like a car radiator, and it's a metal box, and in there is a radiator where the hot water comes in from the boiler. Well, it can be from the gas, the propane backup, or the wood boiler. But water comes in at about 160 degrees, goes through the radiator, and then right behind the radiator there's a fan, electric fan that sucks air from one end and blows it through the radiator. And on the other side of the radiator there's louvers that when the fan comes on, the louvers open up and it just spits warm air. But that effect doesn't work at the speed of that air going out, because when you move air, it feels cool. So the air isn't rushing like it's knocking your hat off or anything, but at the speed that it has to work to reach the far end of the greenhouse, the air that the temperature of that air by the time it gets there is going to be cool if that water isn't at least 130 degrees. In a floor system, like you said, the radiant floor system, where you're passing it through PEX in a concrete bed, it's actually buried in the concrete. The temperature of the water can be 85, 90, 95 degrees, because it's warming up this huge piece of thermal mass, which isn't losing. I mean, it's oozing heat out, but it's not like it's blowing it out into a open air space that keeps on asking for more and more and more. So it's sort of a contained and insulated. It's insulated at the bottom and the sides, and that thermal mass can absorb a lot of heat. And once it's filled, it holds it for a long time.
So much more comfortable.
Yeah, it is on the feet. Yeah.
To follow up on my question.
Oh, I'm sorry.
Tap off the line coming out. Where does that water circulate?
Right.
Well, you have to have a pump, and you pull it back out and then feed it back in.
So that would involve 2 pumps?
Yeah.
Okay.
Yeah.
Okay.
Yeah.
With very small pump.
Yeah.
For that little space.
Mm-hmm.
Yeah.
Yeah, it wouldn't be a big deal.
Where does it goes back into the water supply?
Yeah, it goes back into
so
this.
You end up using.
Yeah, using it anyway. Yeah, it gets heated. When it gets reheated by the solar or whatever, it's gonna be replenished.
Okay.
And those the controller that controls the whole thing, they're not that hard to hook up.
No, they're made.
Well, what's exactly the name of it?
That particular one is called Eagle Sun, but you can just look up solar thermal controller, and there's various manufacturers. Yeah, there's many of them, and you can also hack them. Remember we talked about I was talking about the Instructables website. There's a temperature control unit that's available for about $40, and then you can re-circuit that to make it do a lot of different things, and you can do that. But if you don't want to go to that trouble, you can buy the thermal controllers at the solar supply. There's several solar supply stores online that have perfectly reliable things, and they sell retail. And what they don't really provide you with is that kind of hands-on. I mean, that kind of really particular service.
Some sites purposely make this stuff more complicated than it is because they want you to buy theirs.
Yeah. Well, yeah, that's true.
They
Yeah.
want you to think you don't know what you're doing.
Right. Yeah.
Call them.
Well, and also some people don't want you to call them, and they're just like, our prices are low, but we're not advisors. We're just selling you this stuff. That's all.
Exactly.
Don't call us about it. That's a lot of reason why why people only sell to dealers, because they've been trained and they have and every year they have more experience. Yeah. Right. Yeah. Yeah, and that makes sense too. I mean, it's just a matter of how you want to approach your business. But the control is very simple. It's not it's a DC system, so it's just one wire. There's 2 ports. There's 2 wires for the collector. So one goes up to the thermistor and comes back, and goes into this. So this comes out of the collector and back into the collector ports on the controller, and then the other one right below it is the storage ports. Back out into the storage and back again. And then on top of that, in that particular one, and in most of them now too, there's a phone line, so you can do your reading of the system from remote. You know.
So would one temperature would one temperature override the other one?
Well,
if it was too cold up top to heat.
Well, it won't, the pump will shut off then.
Okay, so then even though it said turn the pump on because it's...
Well, it won't say, oh yeah, well even though it says turn the pump on because there's not enough hot water, it can't turn the pump on because there's no hot water up there either. There's no heat up there either. Yeah. So it'll just shut it off. Yeah. And then it's built in that there's one, if it gets too hot, it's just a signal. It says whatever the temperature is. But in the little box, it is managed that if it gets too hot, then there's another circuit in the box that says, this is getting dangerous, shut the pump off.
Yeah.
That's all. Yeah, drain it. If it's getting too cold, drain it. It's dangerous because it's going to freeze. It's getting too hot, drain it. It's dangerous because it's going to boil. And then the temperature of the water is secondary. Your comfort is basically secondary because this other stuff's more important. Yeah. Now what happens is when all that pump stops and all those drain off, then the electric element, if the event was that the water temperature was too cool in the tank, but the pump was still off because it wasn't hot enough at the collector, then the backup element just kicks on, and that doesn't really have anything to do with the control box. That has to do with the thermostat in the actual water heater. It's saying, okay, we're down to 110 degrees, and I need to I need to kick on.
Go ahead. What control box do you like? I mean, price and reliability.
There was one, I just forget the names of them because I knew more about the PV controllers because there's voltage controllers and stuff. But that thing's called an Eagle Sun, but somebody makes it for them. Eagle Sun, yeah, that's manufactured.
Run on electricity?
Well, the box is fed. Yeah, it's fed 110, and the 110 circuit is controlled and then continues to be fed 110 to the pump. So the box has the plug-in part, goes into the box, goes through its circuitry, and then out 110 for the pump. But the other two controls for the sensors, for the sensor controls, they're DC, they're low voltage DC, direct current.
Right, but that's not the main box.
Well, it's all in the main box, but there must be a little transformer in there that.
I'm just wondering
yeah.
To get, something that's on all the time.
Yeah.
Being off grid, it's nice.
Yeah.
Not have a plus with the I'd like to stay with the DC.
Well, then you have to use a solar panel. That would be another way to do it. Just everything controlled with a DC supplied 12-volt panel or 24-volt.
But I mean the control box. Do they make one that's?
Yeah, I'm pretty sure they do. I don't know for a fact, but I'm almost positive because they do have a lot of off-grid products.
Okay.
Yeah.
Even a pump, I think you can get a DC.
Oh,
pump.
yeah, all over. There's a lot of DC pumps.
So
Yeah.
if you have the DC pump, you don't need to.
Yeah.
Pumps
you
are
don't need
actually
to
more
deal with AC at all. Yeah.
powered by DC,
Except for
right?
the
Yeah.
control box.
Yeah.
No, they don't have to use that either. Yeah.
The circuit
Control box.
for the control box can be managed with DC as well as AC. I mean, it's just a matter of changing it down to DC. That's all.
Almost all electric circuits are DC.
Yeah.
And
they
with
have
the inverter.
Yeah.
It makes DC off the 110. The only reason it's 110
Yeah.
is you got to get it from here to there.
Yeah, that's all. Yeah, that's why it's
Once
AC.
you get to your house, TVs are DC. Most all your appliances.
Yeah,
are
computers,
DC.
all that stuff. The printer. That's what those little transformers are. Those little black boxes.
Well, I was just wondering what controller might be a better off-grid option, I guess.
Yeah, I think the best thing to do is just look online and just look for a DC thermal solar controller.
Okay, but they may have the high limit thermal control.
Maybe, yeah. They have the control box all set up for that.
Okay.
Yeah.
Awesome.
That's what I hear with Backwoods Solar.
Sure. That's where I got a lot of my stuff.
Yeah, they
Oh yeah, I got
focus
that.
on.
Yeah.
Oh, okay. Yeah, they
Yeah.
focus on off-grid. So
Yeah, but they don't necessarily have a lot of thermal. They have a lot of PV electricity. They don't have a lot of hot water stuff.
No.
But they do sell like appliances and things that are like propane-powered stuff and off-grid stuff.
I thought they had maybe expanded into that.
Well, they do, so they don't have a whole lot of it.
And I have an inverter, but one thing because I was circulating my water off my wood stove underneath my concrete floor, and one thing I realized when it's winter and it's really gray out, it's eats up a lot of your power, even low voltage.
Right. Yeah, it doesn't take much to pull. Yeah.
We have a few really gray weeks.
Yeah.
Sun's low.
Yeah, like we have battery backup. We're grid tied here, but the little shack at the end where that power line's coming in, that has 16 720 amp hour deep cycle batteries in it, so we can, when the grid goes down, we still have power.
Yeah, that's key. That's nice.
Yeah, it's rare, it's expensive, you know, but it's a good option to have, because the grid, when you're grid intertied, once the grid goes down, your system is down too. Even though you have the panels and everything, it doesn't work.
Yeah, that's what everybody thinks. That in fact, I remember putting panels on people's houses. Like, I just want power when the grid goes down. It's like,
this isn't doing
it. You didn't buy batteries. I'm just the installer, but you didn't buy batteries.
Yeah.
I mean, you better talk to my. But now I'm doing off grid.
Yeah. So people. And it used to be, you know, it was funny. I think the guy was very involved with off grid. You know, met many people in my businesses that you know were just like we are. We're questions, and I do this, and I live off grid, and the thing that kicked solar, one big thing that kicked solar into the mainstream was the grid tie, because that opened, people had no concept of homesteading or off grid or anything, but all of a sudden
they want to get rid of their bill.
Yeah, they want to get rid of their bill. That's money is always going to talk. You know, that's the way I always approach discussions, is money, because then everybody listens. You know, almost everybody. So that got it out there, and now I see a migration more again back to off grid.
Or a hybrid.
Yeah, or a hybrid. But I mean, a lot of people are really. I think he mentioned it before. A lot of people are thinking about the economy and political systems and how this is all not going to continue on like this forever.
President Trump.
Yeah, and all that. I mean, you know, and even people who are ambivalent about it don't see Trump or Clinton as options, so they're thinking this cannot go on forever. So off grid, yeah.
There's just no power.
Yeah, and those transformers are, you know, in the generating stations where they actually, the dynamos and all that stuff they use in the big power stations, and the transformers, the step down transformers they use from the they use like megavolts in the generating plants, and they step it down several times before it gets to the 220 the 220 that we use. Those things are not like, they don't have them stock of them just sitting. They take time to build. They're very expensive, and so if a solar flare happened, you'd have every power company, you know, Duke and you know, American and oh sure they do, yeah, big enough to do it, but it'll blow those things out, and you're going to have everybody on the phone, which isn't going to work anyway, but everybody on the phone saying, I need a transformer of this scale, and they say, oh, sorry, they take 6 months to build, and we've already got a back. Yeah, right. Yeah, and they don't. They're so expensive. They don't normally blow. Yeah.
In the whole country. You don't have to worry about 6 months later.
Yeah. Oh, it's, you know, it's crazy. But when people bring it up, other people look at them like they're nuts. You know, but you know. Yeah. I had a fellow that was going to do some writing that is was actually a research scientist, but he is involved in the power industry. You know, the power, like, you know, Duke and, well, not Duke, but like that. He lives in New England, but you know, he said this whole thing is a real issue, and you know, certainly don't want to talk about it, but it's really something in the back of their minds, because what are we going to do? That's what they're saying. What are we going to do? You know?
Half the Northeast blacked out.
Yeah. Oh yeah.
What, 7 or 8 years ago?
Yeah.
With that tree branch in
Yeah, right. Or Canada, or whatever it was.
The monkey in India? Or
yeah, it fell on the thing, and yeah. Yeah, it's very.
On the other side of this, you hear about Portugal went 3 days.
Nothing.
Total alternative energy. I mean, ran.
Yeah. Oh yeah. Well, yeah, they do. Germany every year they do that just to show they can do it. You know, on a fairly, in the summer, of course, you know. And then they do just one full day of you know, because they already have like 8% of their new construction has to be renewable energy. It's by law, and then somebody else just did.
California just said all residential must have X amount of
solar
per square foot of house.
Oh, well, that's what they do in Europe, you know. But some other European country did that same thing. Well, besides Portugal, another one too. He just said that.
California will happen here.
Yeah, eventually, yeah.
So they're saying.
I think the Netherlands, I think it was, did some kind of a thing like that, or Denmark, one or the other. It was one of those.
In the building code.
Yeah. Oh, they'll have to build it, yeah, because California comes first usually, and we follow.
In Tennessee, they're actually working to put solar out of business through a TVA. They're making these grant things.
Oh yeah, that's happening all over.
Power companies do not want solar.
No, they don't. No.
They're doing everything they
can to stop it. Yeah.
The only reason it's happening is the government mandated they must do it. If they didn't have to,
of course they don't want to do it. Yeah. Well, they did try Duke Energy actually in the early '80s. They did a pilot program. It was not public. It was a private thing. And the only reason I knew about it is because some of the guys I used to work with went into the solar installation business, and they were the only ones around here who did that at the time. So Duke hired them. Way out in the Pisgah Forest in the Transylvania County, there's a outward bound location, not an office, but it's a facility. It's not that big. It's like a house. And they didn't want to be running power lines. They were having calls to run out there all the time to fix, a tree falls on the line and stuff. So they got an idea that say, what it would take to have somebody install solar panels and treat this as a pilot model to see, we'll still sell you the power. We'll pay for the panels. We'll pay for the installation. We'll pay for the maintenance. And you still pick the phone up and call us. But all that's going to be generated by off-grid photovoltaics that we own. And I guess they didn't like it because they didn't continue with it. But they actually did this test and they had it going for a couple of years.
Were they making less money? Or
I don't know. The people that are doing the installation weren't privy to that stuff. No, they didn't. They just didn't know.
Got rid of those numbers.
Yeah. Yeah, I don't know.
Consulting with Innovative Solar, it's based out of Asheville.
Uh-huh.
And they don't do a system that's less than $150 million.
Yeah, wow.
10 megawatts. And
Huh.
So all they do is manage the contractors. So one element is managing the contract with the power companies, and the other element is managing the contract with the physical contractors that build the system.
Yeah.
So they don't physically do anything. They just manage.
Yeah, they manage the flow of
between the contractors.
energy between the two.
And so in their discussion, I dealt with them on the contracting side of the physical, go out, put the panels in, do
yeah.
that. On the other side is dealing with Duke. Duke will do everything in their
To
power
make it not work.
To make it not work. If they can delay the system by
Yeah.
a month or 3 months,
Yeah.
it makes it financially not attractive to go do it.
Right, yeah.
So they have more of their staff is dealing with the interface with the power companies than dealing with the actual contraction of this, because they have to, every paperwork has to be filed exactly. They misspell something.
Yeah,
the
yeah.
contract comes back.
Yeah.
So that's what's making the system work, and it's only the government regulation that Duke Power or whatever power company must interact with this renewable energy solar farm.
Yeah.
To bring power onto their grid, and it's really an adversarial relationship that it's very difficult.
I'm sure Big Coal has deep ties with these
and
giant.
then there's the next element is these companies that are just Google Innovative Solar and see all the systems they put on. They have 80 systems that are 150 million plus in the works right now. They did $4 billion of sales last year. They're going to do $6 billion this year. So big deals. A delay of a few months makes a big difference. So those companies are against the residential solar.
Yeah, yeah, right.
So the residential solar, I believe, is going to go away. And there's going to be community solars where we're going to go do a system, and we're going to buy 10% of it or 5% of it, and they'll sell power to the power company, and I own a 5%, 10% share in that little solar farm. That's the way.
Yeah, that's what it looks like. I've heard the same thing.
Having solar on your roof and a little inverter and good time.
More distributed generation on a small community scale. That seems more like district heating works in Denmark and Sweden. They have district heating where there's one little heating thing that distributes just to a few blocks around.
Big scale of a farm, and they can manage it, manage the power factors going in and out. These little bitty individual residential.
Yeah, there's no control.
Pain for
and not as efficient, really. I mean, that's but they're independent.
So like First Solar, big Sam Walton company.
Right. Yeah.
They're putting all the legislation that favors
the
large solar farms, and it does not favor residential solar.
No, at all.
That's TVA too.
Yeah.
I mean, that's pretty much who gets the permits.
Yeah, it's just control. It's the thing about our solar thermal credits in North Carolina. It sort of adds on to what you just said. They dropped the credits for solar thermal, for electricity, for a lot of stuff. It's going to come back, but I have a feeling that the PV part of it, the electrical, is not going to get the credits. Only the hot water, only solar thermal is going to get and maybe the biomass and stuff like that. But yeah. So the PV is like now we're not going to.
political decisions. Basically.
Yeah, I would think so. And I also remember that our governor used to work for Duke, and you know.
Oh,
Yeah.
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 Well, maybe he'll be Trump's vice president.
Yeah.
That'll save
Yes.
us. I heard that.
I wonder if we're ready to eat. It's 6:32 or something. Or are they going to come out and tell us?
Migrate in there?
I'll try.
Well, I don't want to pressure him because he might not be ready. Oh, okay.
I don't mind.